Wabarakatuh dan salam sejahtera. So today is our first video conference for JIF103 Physics 1 Practical 1A. So first of all, I would like to start off with our academic planner. It seems that there's only one student in our class. Yep. May I know who's in the... Is it in Ipoh or is it in Kota Baru? Yes. Yes. Haha. You are right.
Okay.
Yes.
Can you hear me?
Yes, of course.
I'm from Kota Baru.
Kota Baru. You better bring your chair to that one. Near to the microphone. Take the chair near the microphone.
Okay. One of my friends will come later.
Okay, great. Never mind. So we just have in KB and also in Penang, of course. Okay, so first of all, I will start with your academic planner. So since this is the first, our first meeting for this academic year, so inshallah we are going to have 6 video conference for this course. For this one, we will discuss about relativity of time. But we see how we go along, yeah? Our next video conference, we do relativity of length. And the third one, we are going to do relativity of simultaneity. The fourth one, perhaps, is going to be momentum, energy, and mass. Depends on the situation. If not, we'll do the particle nature of light. And 6 is matter wave. We'll see how we goes, yeah. This is our tentative schedule. This one you can download it from the web, our e-portal. Okay, as you know that I'm your course manager. So this is about modern physics. Basically, I hope all of you has received your textbook. So our textbook is something like this, isn't it? Do you have this textbook, all of you? Is it the same? Okay, great then. Okay, so we are going to cover chapter 1, chapter 2, 3, and 4. Can you see the screen? Is it clear for all of you or is it blurred? Is it very clear?
It's clear.
Oh, great then. Switch it off then. Okay, so you are going to we are going to go over for this academic year 4 chapters. I guess I'll make it bigger so that it's easier for you to see. So chapter 1 is on relativity. Chapter 2 is on particle property of waves. Chapter 3 will be wave property of particles, and chapter 4 will be atomic structure. But for the atomic structure, there's some similarity with the one that you are going to learn in JIF104. So it's you are learning the same thing twice. So it's no problem then. But for your continuous exam in January or February, you will be tested on only chapter 1, relativity. Okay, relativity will be questioned in your continuous exam during intensive course between 21st of January until 10th of February. So it's somewhere along that time. Yeah. You are required to do 3 lab work. Uncertainty analysis, which is, I guess this is very fundamental. All of you need to know this one because this one, you are going to use it in all of your lab work in USM. Yeah? How to calculate uncertainty for all your measurements. Next, experiment 2, you are going to do exploring motion, and 3 is light interference, which will help you later in when learning wave properties of matter. Okay, and you are required to hand in your lab reports. Make sure you do all your lab reports and submit it to me. Yep. Hopefully at the end of the intensive course. Because if we give you the leeway to take home, there's a possibility of a few of you not handing in your lab report. So I hope you can do all the 3 lab reports while you are here in the intensive course to save you time. Of course, we are going to have 6 video conference. I guess it's 3 before intensive course and 3 after intensive course, isn't it? Or is it 4? I'm not sure. Have you all seen the schedule? The video conference schedule?
In the only 3 session in our schedule.
Okay, so 3 sessions before the intensive course and another 3 after the intensive course. So I guess we are going to cover momentum, energy and mass during the intensive course. So session 4 will be particle nature of light. Never mind. Tomorrow I'll reload a new academic planner, because since there's only 3 sessions. Okay, and then matter waves. Okay, some more. Okay, how are you going to be graded? Final exam will carry 60 marks. And coursework will carry 40 marks. Assignment will be 5%. Assignment 1. Assignment 2, another 5%. Continuous exam, 20%. And practical, 10%. Okay. But normally, there will be some assignment that will help you in your continuous examination. So for each video conference, there will be assignments that I would like you to do. The function of this assignment is to supplement your continuous examination assignment results. Normally, student didn't do well in the continuous examination. So I'll give you extra assignment after each video conference to supplement your continuous examination marks. Right. So final examination will be 3 hours covering all the 4 chapters. And also the extra notes covered in e-portal. Okay, of course, I did say that there's 2 assignments. So, your assignment, you are going to upload it online to the e-portal. I guess, do you know how to do this one? Have you logged into the e-portal yet?
I think that about the e-tugasan session.
The thing is, sorry, I couldn't hear you.
E-tugasan
Yes,
session.
yes. Yeah, you have a label there, isn't it? An icon at the topmost. Yeah. So you have submit your assignment there. So you make it into a PDF format. Normally in our work, Microsoft Word, you can just save it as PDF format. So and just send it through to e-portal. Of course, yeah. Please make sure you submit it on the correct date, because we can easily detect whether it's over the time frame or not. So your first assignment due 1st December, second assignment due on 1st March. Okay, your marks will be downgraded should you miss the submission deadlines. Okay, continuous exam will be 1 hour. But sometimes I do give extra half an hour. So 1.5 hour. Kasihan. During the intensive course will be 21st January until 10th of February. Okay, I guess that's all. Do you have any question? If not, we go straight to our class about your academic planner. No question at all? Okay, great then. So let's go to our class. Any one of you bringing your smartphone today? Can I see your hands up? Anyone bringing your smartphone? Okay, great. Then we can have an interactive class. Okay, so today is about relativity of time, which was coined up by Einstein. Okay. Let's say, ni pukul, at 6 o'clock. So if 6:01 minute, the question is, does the time interval between two ticks of our watches will always stay the same? Does the time interval between two ticks of our watch will always stay the same? Adakah dia akan sentiasa sama selama masa di antara dua tick pada jam kita?
Yes.
Give your reason. Sat. Lajunya. Okay. Go to this website. http padlet.com/Farida/time interval. Pergi kat situ. Double click on that one and give your opinion. Write your name and then give your opinion. Okay, for those of you at home, you can also participate in this one. Okay, just go to this website and give your opinion. Okay dah. So I'm going to go to that website. Oh, tak nampak lagi. Do I have to refresh? Tadi saya punya apa? Time interval ke apa? Let me see. Okay, Azizul kata no. Okay, your reason, Azizul? Just write it down kat situ. Give your reasons why you say no. What about the others? Yang ni apa? Yes, because the radius is the same. Nurul Ain, radius? Why do you say radius? Does radius has anything to do with time interval? Yes, because the radius is the same. Kenapa Nurul Ain kata radius is the same? Okay, Azizul say, no, it's not the same because it changed because of mass. Oh, it has something to do with mass, ya Azizul. Time. Okay, tak apa. Nanti kita tengok ya. Whether it's not the same because of the mass ka, or is it not the same because of like Nurul Ain say it's because of the radius. What about the others? I can see a few of you. Let's see, let me refresh it. Zaim kata, yes, because if not same, there will be error in the whole. Oh, so Zaim said, the time interval will always be the same, if not error. Okay, sama? Okay, tak ada lagi yang lain. Itu saja. 3 orang saja bagi opinion. What about the rest? Because I can see all of you having your smartphones. Tak masuk lagi you punya. Yang lain. Siapa punya yang dah hantar tapi tak sampai lagi? So, if we see here, that's two groups of student, one saying yes and Azizul saying no. I mean, the time is not going to be the same because it depends on the mass of the object. Nurul Ain say because the radius is the same, and Zaim say there will be error in the measurement of time, it seems. Okay. So, Zaim, calculation will be always wrong if time is error. Okay, we'll see, yeah? Okay, let's go to our PowerPoint again. So now, let's see, yeah? Let's say we have a clock 1, yeah, showing pukul berapa ni, ya? 12.55. No, 11.55. And then we have another clock. Both of these clocks are synchronized, meaning they have the same time. Yeah, both clocks have the same time. Okay. And let's say we have another clock C3. Yeah, when it reaches C1, it shows the same time. Okay, let's say C3 is moving very fast at speed V. Okay, when C3 at C1, yeah, passing at C1, it shows the same time as C1. If you look here, isn't it? Showing the same time. So all three clocks are synchronized, meaning showing the same time. Okay. Agree? Do you all agree? It's showing the same time? Okay.
Yes, doctor.
Okay, now. Okay, let's say C3 is moving very fast. Yeah. And then it passes until it reaches C2. Okay. The question is now, is the time shown on C3 earlier than, the same, or later than the time shown on C2? Time on C3, is it earlier than, the same, or later than the time shown on C2? Cuba fikir dulu. Fikir. Okay, dah fikir dah? So, Penang says?
Same.
Penang says it's going to be same. Why?
Doctor,
Yes.
if the same zone, we get the same time.
Oh, same time zone.
Yeah. If the different time zone, we get a different time.
Oh, so it has something to do with the time zone. Okay.
Maybe, doctor.
Maybe. Okay, never mind. So that's Penang's opinion. It has something to do with the time zone. If it's the same zone, it's the same time. Okay, what about those in Kota Baru?
Doctor,
Yes.
in my opinion,
Yes.
V is very fast.
Yes. Uh-huh.
Because of that, as the C3 passes a C2, so this so the time is similar to C2.
So C3 is going to show the same time as C2. Is that
Yep.
what you're trying to say? Is that what you are saying?
Yes.
Oh, okay. All right. So why do you say it's the same time?
Because V equal to distance over time.
Uh-huh.
But V is very fast. That's why C3 is equal to C2.
Okay, because it's
I
moving very fast, then C3 is equals to C2. Okay, if it's go very slow,
okay.
okay meaning?
It's all about V as a formula. V equal to distance over time.
Yes. So it's about the formula distance over time. Lepas tu, if it's slow or is fast, it's still the same. So it doesn't matter whether C3 is moving very fast or C3 is moving very slow. It will still show the same time. Is that what you are trying to say? Since it's always V is equals to D divided by T. Is it?
Okay.
Is that what you are trying to say?
Referring to that formula, that's why I in my opinion, the C3 is equal to C2.
Okay.
But V is constant.
Since V is constant, then V is constant and V is equals to D divided by T, then it's always the same no matter whether it's moving fast or slow. Is it?
Yes.
Okay. Right. So what about our friend in Kuala Lumpur? Yes. On your mic.
Can you hear me?
Yes, of course. Yes.
From our opinion, the time is earlier than C2
Oh,
because the change of velocity.
because of the change in velocity, the time on C3 will be earlier than C2. Is it?
Yes, correct. From our opinion.
Oh, okay. So we have a different opinion, yeah, from all of you. 2 against 1. Yes, no. 2 against 1. Just now also 2 against 1. So let's see, yeah. Who's the one correct then? Then we see, yeah. Different students have different opinion of what you are going to learn. That's great. At least we know it's something to do with mass. It's something to do with radius. It's something to do with time zone. It's something to do with V is equals to D over T. And its speed is constant. And then it doesn't matter whether it's going fast or it's going slow. Now we'll see. What is it exactly, yeah? Okay, to experiment, let's use a light clock. Yeah, what is a light clock? So, switch off your microphone, Kuala Lumpur. Have you switched off your microphone? Okay. All right. A light clock is we are using a light source, and then we shine it to a mirror. So the events are light being shown, yeah, lampu dikeluarkan, cahaya dikeluarkan, and then it's reflected from this mirror, and then it's being detected by a light detector. So the events are light being emitted and then light being detected. Okay. So the time interval between light being emitted and the light being detected. So that's the time interval between those two events. And the distance between the light source and the mirror is L0. So we are going to measure time in terms of light being emitted and light being detected. So that's the time interval. Okay. So kiranya we are using a proxy lah, a light clock, to measure time interval between two events. See, but these two events occur at the same place ke tidak? Is it occurring at the same place? Is it occurring at the same place? Yes or no? Event light being emitted and light being detected. Is it at the same place?
Yes, Doctor.
Okay. Kenapa? Kenapa I really stress benda ni? Because this is very crucial for you later on when you would like to determine proper time and improper time. Okay. When those two events occur at the same place, or if we just use one clock to make the measurement, it's called the proper time. So, if this clock, light emitted, event 1, and light being detected is event 2. So, if event 1 and event 2 are at the same place, yeah, maka it's measuring the proper time. Okay, tulis somewhere in your notes. Yeah. Proper time is equal to two events occurring at one place. Okay. Ataupun two events being the time interval between two events measured using one clock. See? Yang ini kan dia guna satu clock saja kan? Because place of emission and detection is the same. Boleh ke everyone? Is it okay with all of you? Did you get what I'm trying to say? Two events, the time interval between two events, light emitted and light being detected, occurs at the same place. So we just use one clock to make the measurement, then it's measuring the proper time. Okay. Now, kita nak tengok, we are going to see with your own eyes, yeah? Is there any difference in the time interval when there is a change in speed? Ya. Mula kita tengok dulu, adakah fenomena time is going to be the same ataupun different ni? Is it always the same? Okay. Let me show this simulation. I've uploaded this simulation at the e-portal so that you can play around and exploit, yeah? Since there's differing opinion among you, yeah? Okay. Now, look at this value. Yeah? Let's say at 0 speed, when both of the light clock, let's say this is on a train, this is observer looking at the light clock. So, this observer is measuring the time interval of what's happening to the light clock on this train. Okay? This lady is measuring this time. If both of it at rest, not moving, so what you see, is it the same time or different time? If both not moving, is it going to show the same time or different time? Anyone? Just answer. Yeah, answer. Yes. Yes. Don't waste your time. Kita time very short.
The same time.
Okay, the same time. Okay. Yes. Same time, isn't it? You are correct. Now, let's say the train is moving. You all nak nak what speed? You all nak berapa? 0.5 C? C ni is the speed of light. Do you want 0.5 C? The speed of light, or do you want 0.6 C? Which one? Any of this value? Just say. Which one you want?
0.5, Doctor.
Okay, 0.5. Okay, now, is it going to show the same time? Is it that this girl, this clock, will it show the same time for both cases?
To be same.
It will be the same.
Should
Okay,
be.
Penang kata should be the same. Is it? Yes. Okay, what about... Same angkat tangan. Is it going to be the same? Kalau tak same, angkat tangan. Okay, same. Kota Baru? Kota Baru tak same. Kota Baru same
Not
atau
same.
tak same?
Not same.
Okay, so 2 against 1 again. 2 pusat wilayah against 1. Now kita tengok. Ke kita patut bagi markah kepada orang yang betul, isn't it? Nak bagi markah ke tidak? Selamat lah sebab datang video conference ni. Nak bagi markah ke tak bagi markah? Nak bagi berapa? 5. Kita bagi 5 lah. Kalau siapa betul. The correct guess. Okay, now kita tengok. Same ke tak same? Same ke tak same?
Tak same.
Yes, tak same. Yes. So, kawan kita yang kat Kota Baru tu siapa namanya?
Zaim.
Zaim. Okay, Zaim. So, Zaim get the mark. Okay. Okay. Tak same. Okay, now kita nak tengok pula ya. So, adakah fenomena ni macam ini saja? Or is it at 0.5 saja? Alah, mungkin at 0.5 saja, isn't it? Not necessary for all speed. Okay, Cik buat dekat you punya notes, buat ni. Let's see. Skip. Okay. Okay, cuba ya. To the next slide. Saya cuba write down on your somewhere. Ni buat this table. Okay, relative speed. 0, 0.2, 0.4, 0.6, 0.8, 0.98 C. Saya tulislah, scribble somewhere. Okay. Kita nak tengok ground observer measuring the time interval of the moving light clock. Berapa nilai dia ya? Okay, dah sudah ke? Now, let's see ya. Okay. Okay. So, kita nak start dengan kosong. Kosong kita dah tengok tadi kan? It's the same, isn't it? Okay, if both at rest, then it's the same. Next, kita pergi kepada 0.2 speed, isn't it? So, catat pada your ni. So, you nampak kan? Okay, catat pada you your table. So 1.021, isn't it? Okay, now kita go to 0.4C. So you get berapa? 1.091, isn't it? Now we go to 0.6. So you get 1.250. Then we go to 0.8. We get 1.667. Okay, what do you think will happen to 0.98C? The time interval. It will be? So it will be berapa?
2, Doktor.
Oh, it will be 2. Okay, let's see whether you get it right this time round, yeah? Dah terkeluar dah. Dah tak muat. Frame tu. Ada lebih daripada 2 dah, Nurain. So it's 5.025. So what can you say, yeah? Time interval ni. What can you conclude? If you look at your table ni, what can you conclude? Ataupun saya bagikan rendah sikit kan, supaya you boleh nampak benda tu. Okay. What can you conclude? Daripada table you tu, apa boleh conclude?
The increased speed occurs the higher time interval.
Aha. Higher time interval maksudnya apa? Time interval tu dia get apa? Higher tu ialah memang you boleh guna perkataan higher, tapi dia ada word dia sebenarnya. Jadi time tu dia jadi macam mana? Detik. Dia jadi longer, isn't it? Time interval jadi longer. Jadi time interval jadi longer bermaksud, what does it mean? Kalau kata age kita kan, time tu jadi longer bermakna, time interval tu jadi longer bermakna, kalau time interval jadi makna longer, kalau ikut age kita ni, time interval longer, macam mana? Jadi kita akan, we will
to be older.
Kita akan jadi older, cepat older, macam tu.
Slow.
Kita slow to age, isn't it?
Yes. Slow to be old.
Yes. It's great, isn't it? We can be younger than our adik. Isn't it? If we travel very fast, we can in fact travel than adik kita yang masih kecil-kecil tu. Kita boleh awet muda lah sentiasa kan. Isn't it? Longer time interval means we age slower kan. So, jadi macam mana kita nak tahu siapa yang will age slower? Sebenarnya ya, yang ini, since ini dia akan measure apa saya kata tadi? Proper time kan? Sebab yang proper time sentiasa tak ubah, isn't it? Kan? Yang cuba ubah kalau kes apa? Yang measure time at different places, isn't it? Nampak tak? Kan? Ini emitted, light emitted. Ini light detected. If two events, ya, emission dengan detection dia different places, maka kita akan get this dilated time, isn't it? Boleh ke? Do you get what I'm trying to tell you? Okay. Saya cuba cakap balik apa yang saya cakap. Zaim, tolong cakap balik apa yang saya cakap.
Sorry, Prof. I cannot rephrase your words.
Just rephrase it. Okay, never mind. Rephrase it. What did I say just now? Mengenai time macam mana yang akan dilate. Time yang macam mana yang tak akan dilate. Time yang mana yang akan dilate. Which one?
Time that we move between 2 points, it will be dilate. But if at the same time, at the same point, we but if that point is not moved, it will not dilate.
Okay. Dia macam ni. You have to be really berhati-hati dengan perkataan move. Ya. Kadang-kadang ya train ni memang move. Siapa kata train ni tak move? You katakan time kalau move. Perkataan move tu akan confusekan you. If the event yang emit and detection at the same place, two events happening at the same place, or using one clock, naik turun, same clock to measure the time interval, satu clock saja kat sini, maka that time won't change. Ya, time yang nak dilate hanyalah time yang the event for emission and the event for detection at different places. Ya, different places. Yang itu, the time will be dilated. Why do I really stress benda ni? Because most of the student won't be able to answer or solve relativity punya space-time problem if you cannot get the idea yang I'm telling you now. This clock, two events at the same place will measure proper time. Dah tulis somewhere dah kan? Now you add another one. If two events at different places, ya kan nampak ni kan? Event yang dekat different places saja yang akan berubah time dia, isn't it? Get dilated. Sedangkan when the time at the same place, two events at the same place, the time doesn't change. This is called proper time. Yang time two events at different places is called improper time. IMPROPER. Improper time. Sesat. Yang ni tak boleh nak tulis. Okay. So, ni proper time, see, is ini dilated time interval ataupun improper time. Okay. Now, can somebody tell me macam mana nak tahu proper time? Okay, saya akan bagi marks. Who can say it out? Okay, Zaim dah dapat 5. Siapa nak cuba?
Doktor, saya nak cuba.
Okay, orang lain.
Proper time when two event occur at the one place.
Okay, what about improper time?
Improper time when two event occur at different place.
Okay, betul lah tu. Okay, 5. Okay, 5 markah. Alright, senang saja kan? Okay, lepas ni, if you nak solve soalan ini, senang saja. Bila you baca soalan, tengok ya. Dua event ni same place ke tak same place? Pada orang tu. If then same place, then you know is measuring proper time. Proper time dia takkan ubah. Tapi if in proper time, the two event different places, then it's improper time. Okay. Ada apa-apa soalan nak tanya saya setakat ini? Oh, time dah nak cukup. Okay, any questions?
Hi, Doctor.
Yes.
I got one question. Actually, how can we look more younger if the time interval is more longer lah?
How can we be younger? Okay, how can we be younger if time interval is longer? Let's say, for this person on this train, since it's measuring this one, the time interval 1 saat untuk dia. Tapi for this person, macam mana saya nampak asat-asat like this. Nanti ya. Let me go back to this video conference. Kita ada macam mana? Let me show you a simulation. Then you can really faham what I'm trying to tell you. Simulation ni saya dah letak, I put it in the e-portal ya. Macam mana yang boleh jadi younger? Okay, clock on Earth, somebody on Earth ya. And then clock on spaceship. Okay, ya. Let's go and see ya. Tengok Okay. So what can you see? Clock yang on Earth dah tunjuk 60 minit. But the clock on the spaceship shows 26 minutes. Jadi age, the one on Earth will be older, isn't it? Because 60 minutes has gone by. Sedangkan on the spaceship, it's only 26 minutes gone by. So, katakanlah, So, okay. So, let's say I give you another brain teaser, ya. Senang je. Ni, kan? I mean, always cerita Einstein, isn't it? Every time, twin paradox. Kata dua twin, satu pi angkasa lepas, travelling near the speed of light. Ya. Kemudian dia calling dia punya sister, suruh balik. Ya. Then bila dah nak balik tu, dia dah tua. What about the sister? Is it the sister is going to be old also? Or what? Cepat bincang antara you all. Time is short already. Time dah lepas dah pun anyway. So cepat.
Still younger.
Okay. Younger. Itu Penang. What about Kuala Lumpur?
Younger than her brother.
Yeah, daripada brother dia. Okay. What about ni? Kota Baru.
Twin is not older as the other twin.
Okay. Betul lah tu. Semua dah betul kan? Isn't it? It will stay young kan? Because pada dia, both event are at the same place, isn't it? Dalam kapal terbang dia. The same place. But kawan yang dekat bumi ni akan nampak dia ketika dia pergi 1 o'clock, one event, and then bila balik, another event kan? Lain. Okay, it was younger. Okay, at least everybody setuju that it's going to be younger. But why is it younger? Yang itu assignment sidang video pertama. I will upload it tomorrow. Then all of you answer it to help you punya continuous examination punya marks. To boost it up. Yang itu 20%, isn't it? Okay, I'll give the question and then please answer it. Saya akan bagi time frame. Lepas time frame tu, you cannot upload anymore. Normally saya akan bagi 1 month for you to upload. Okay. Video conference for this academic year. So I can see that several students somewhere in Kuala Lumpur, in Penang, Melaka. There's nobody in Ipoh. Okay, so I have 1, 2, 3 groups then. Okay, basically we are going to talk about Einstein space-times, but this time we are going to discuss about length, yeah? So basically what we are going to do today, we are going to discuss about these questions. Is length absolute? Is there any evidence to substantiate the argument? And lastly, how to calculate length contraction if there's any. So there's about 3 questions that we are going to discuss today. I hope at the end of the day you are going to be convinced with whatever our discussion is, because it's very important for you. Okay, let's start off with the question, is length absolute? Actually, a standard meter, what does it mean by 1 meter? Yeah? So, internationally, it has been agreed that 1 meter is actually the time light travel in vacuum in 1/3 times 10 to the power 8 second. So, that's 1 meter. Yeah. Jadi our 1 meter is actually the time light travel in vacuum in 1/3 times 10 to the power of 8 second. So you see now, the definition of time is no longer something that you measured with a ruler, but now time is something about the time. Now length is something about the time light travel in vacuum. Okay. So now, whatever is in your head now about measurement of length, it's not about measuring it with a ruler. Yeah. It's not about measuring it with a ruler. Ruler, this is a ruler. But actually, the length of a ruler, ataupun 1 meter rule, ya, ruler, ataupun kalau kita nak beli kain, isn't it? We measure it with 1 meter rule, yeah, is actually the standard of it. How do we know it's 1 meter? It's actually based on the time light travel in vacuum in 1/3 to the power of 8 second. Okay. Now, you kena betulkan ya. Apa yang dalam minda tu. Essentially, if measure length is based on the time light travel in vacuum. Okay, boleh? Is it okay now, everybody, with that idea? KL, can I know whether you agree or not? With the way of measuring?
Okay.
Okay, what about Penang?
Okay.
Okay, boleh okay, What about those in Melaka? What about those in Melaka? Okay. Oh, one of our lone friend there, I don't know where you are from. Ada seorang tu yang baru duduk tu, where are you from?
Kelantan.
Oh,
Kota Baru.
Kelantan. Okay. Do you agree with whatever that I say just now?
Yes.
Okay. Make sure now, everybody, yeah? Measurement of length means is based on the time light travel in vacuum. Okay. Alright. Now, issue dia is... Kan, isu dia... Okay, itu 1 meter rule dia. Isu dia... Will a meter rule always be 1 meter? Okay. Will a meter rule, a meter ruler, meter 1 meter punya ruler, will it always be 1 meter? What do you think? Semua ada bawa smartphone ke hari ni? Everybody ada bawa smartphone ke? Mesti punya ada kan. Zaman sekarang everybody must have one. Okay. Question dia sebenarnya is length absolute. Adakah pembaris 1 meter ni always be 1 meter? Kalau dia always be 1 meter means panjang adalah absolute. Absolute cakap Melayu apa? Mutlak. Okay. Kiranya panjang dia tak akan berubah. 1 meter will always be 1 meter. Okay. Now, saya nak tanya pendapat you all pula. Ya? Is length absolute never change? Yes or no? If you say yes, why? Give your reasoning. If you say no, give your reasoning. Pergi to that website, http://padlet.com/farida/length absolute. Okay, pergi dengan your punya smartphone tu. Pergi to that URL. And then you double click dalam benda tu, then give your opinion. Yes or no? Okay, tapi dah URL tu. Those of you at home, okay, you can also go to this URL, and give your opinion. So it doesn't matter whether you are in live telecast or you are at home. Please go to that URL and give your opinion. Okay, so I'm going there, Okay, Azima, KL. Tak ada bagi opinion lagi, baru tulis nama saja. Okay. So, give your opinion. Okay. Tak ada siapa nak bagi ke? Okay, yes. Siapa? Yes tu. Yes, yes. Okay, yes. Indeed. So, yes, yes, indeed. So, your reasoning? Why do you say so? Okay. Okay, Azima, continue give your opinion, your reason why you say length is absolute, meaning it never change. What about the rest? Tak bawa smartphone today? Alamak, sayanglah. I really would like to know what your opinion is. Okay, Salvam, kata apa? Salvam. Okay. Yes. So, saya yes, yes. Saya letakkan satu tempat. Ya. Hafiz. Okay. Hafiz Alus tak? Okay. Yes. Okay. Ni satu kumpulan yes lah ya. Okay. Hafiz Alus tak? You kata apa? Since 1 meter equal to 1 the speed of light, it will vary depend on speed. Macam mana ni apa yes indeed ni? Dia kata yes indeed. Lepas tu it vary pula depend on object velocity. Ni macam rupa langit dengan bumi punya cerita ni. Okay, Selvam kata length will be shorter. Okay, Selvam kata mesti no lah ya. Okay, Hafiz kata no. Jadi kita ada dua grup lah. Ada satu grup kata yes, ada satu grup kata no. Ada yang ini, okay, dah tiba-tiba saling tukar fikiran pula. Okay, silap tadi. Okay, alright. Now I know ada somebody ngaku dia silap. Okay, Nakibah? Azimah dah tukar fikiran ke? Tadi banyak yes. Sekarang dah ada no pula. Okay, so Azimah ni saya tak tahulah dia nak bolang kumpulan mana. Yes ke no ke? Jadi saya buka tengah. Ada satu yes ni. Okay, yes. Masih lagi yes. Okay, ni no. Okay, Azimah pun no. Okay, based on apa? Okay, based on speed. Nakibah no. Okay. Lagi? Siapa lagi nak bagi opinion sikit saja? Jadi kiranya ada 1, 2, 3. No, indeed ni saya bagi nama you. Nanti saya nak bagi markah susah. Bubuh your name. Then I will give marks to you. Siapa yang participate will get extra marks. Okay, Nabila. Okay, Nabila. Apa dia opinion you? Okay, no. Alright. Apa reason dia? Because? Di yes tadi ni siapa ni? Tak tahu nama dia. Tadi no indeed ni cuba bubuh nama you. Put your name there so that I know who you are. Okay, Mizi, yes or no? Okay, Nabiha kata no, it depends on where it is measured. Okay, no. Ada kata based on speed. Ada kata, banyak yang kata based on speed. Subject. So, Hafiz dengan Nabila kata based on where it is measured lah ya. Sebab dia kata will be shorter somewhat. Yang ini semua depend on speed. Okay. Nakibah tak tahu. No saja. Yes, based on subject. Ni group yes. Okay, Mizi based yes. Uzaifah pun kata, rula takkan berubah. No, kata Firdaus. No, it depends on location. Macam mana pula Firdaus? Dan no, no. Depends on location. So, dalam group location lah ya. Dan Kibah ni, dia apa dia reason dia? No apa? Reasoning you apa? Okay, Fik ni, pusat wilayah Pulau Pinang ni apa? Apa opinion you? Dino Indik ni siapa nama you ni?
Prof, turun bawah sikit, Prof.
Lagi, you punya kat bawah. Sorry.
Prof, scroll down. Ada lagi kat bawah.
Ngapa tulis kat bawah-bawah? Okay. Yes, ruler takkan berubah. Siapa nama ni? Yes, ruler takkan berubah ni. Okay, Fik. Apa dia? Cerita dia? Tak ada cerita. Kosong. No, kata Firdaus. Apa reason dia? No ni macam Nakibah. Tak ada reason. Haikal, depend on pressure. Ni kumpulan baru ni Haikal. No, depend on pressure. Lagi? Ada bawah. Syarul, if time like travel. Yes. Okay. Ni Nurul Ain. Yes, we can see at constant place. Okay. Sebab kita tengok every day, it doesn't change ya. Okay. Nakibah, no, based on observer. Depend on observer. Indeed, tadi nama dia, yang Indeed, Azizul. Okay. Azizul, you boleh betul dekat atas tempat you tu. Okey, so kalau kita tengok ya, dia ada dua kumpulan. Satu kumpulan yes. Ya, macam tak confident dia kumpulan yes ni. Kan? Ni macam confident. Yes, ruler takkan berubah. Ya, Nurul Ain kata, we see dia sentiasa constant. Betul juga ya. Tapi ada satu kumpulan kata, indeed dia akan berubah. Ya, satu cohort dalam kumpulan yang kata berubah ni, dia depend on where you look. Okey, jadi kiranya dia depend on reference frame lah ya. Depend on location. Depend on mana tadi? Based on observer ya, siapa yang melihat, dari mana. Ada satu kumpulan kata dia depend on had laju ya. Ada 1, 2, 3. Ini ada heat dengan speed pula dah. Ada heat pula. Tak apa, nanti kita tengok ya. Whether it indeed depend on heat. Okay. Depend on light travel. Okay. So, kiranya depend on speed lah ya. Okay. So, now, Syarul. Apa tu? Tak ada dia punya opinion pun. Apa dia? Okay. Last kita bagi Syarul dengan Fik untuk bagi opinion. Then, we go to the next slide. Okay lah Fik dengan ni. Okay, sebelum ni. Okay lah Fik. Yes, because length refer to, length refer to distance measured. Okay, Syarul kata faster mean shorter lah kot ya. Okay, so kiranya dia depend on speed lah ya Syarul. Okay, Hafizul? Not affected by relative motion. Okay. So Hafizul kiranya something to do with relative motion. Lagi siapa? Yes. Meter ruler takkan berubah. Ni siapa yang kata yes ruler takkan berubah ni? Cik tulis nama you. Okay. So we see there's 2 cohort ya. Now saya nak tunjuk evidence ya. Sama ada berlaku tak perubahan in length ya. Okay. Okay, so now ya, saya nak pergi to the ni slide. Okay. Okay, now ya. Katakanlah ya, spaceship ni tak bergerak. So it's not moving. So this is satu spaceship. Ya, ini somebody on earth ya. Katalah kita tengah tengok ya. Kita nampak spaceship tu, roket tu tengah bergerak. Tengah bergerak. Dia tak bergerak lah ya. Ini kosong C. Kosong C means it's not moving lah ya. Okay. Dia berdiri kat situ ya. Berdiri. I mean is there at that particular position. Kita lambai-lambai. Okay. Now this is at 0C. Now let's go to 0.1C. Ya, dekat 0.1C. So, what do we see? So, is there any changes in the length of the rocket tu? Penang? Penang?
Yes.
Ada ke? Nampak ke? Nurul Ain, what do you say?
Yes, Prof.
Apa ke tak?
Yes, Prof. Ada.
Oh, ada. Oh, you ada. Rasa macam tak ada ubah pun. Okay. Okay, tak apa. We go to a much higher speed, 0.87C. So what do you think about the length? Melaka. Awak Melaka, what do you think about the length of the spaceship? Is it going to be the same at 0 speed ketika dia tak gerak at rest? Ataupun now length dia change? Melakar. Macam mana? Tak tahu. Geling je. Okey, siapa nak cuba? Alah, siapa nak cuba? Who like to try? Kita tadi kan ada 2 kumpulan. Kumpulan yang kata tak berubah, satu kumpulan yang kata berubah. So now, yes KL. On your mic. Tak boleh dengar? On your microphone. Tak ada?
Prof, tak maaf sebenarnya tak faham.
No, tak faham. No, saya nak tanya you. Kalau you tengok sekarang ni spaceship tu, sebelum saya nak tunjuk dia punya animation, do you think length of spaceship tu akan berubah ataupun tidak?
Saya jawab.
Yes.
Okay, from KL, the length will become shorter. The length will become shorter because it moves faster.
Okay, KL kata the length will become shorter. Okay, orang lain? Yang lain? Okay, Nurul Ain? What do you think?
Doktor, yang length tu base pada ketinggian observer dengan roket ke ataupun yang space yang bergerak tu? Sebenarnya saya confused sebenarnya.
Okay, length of spaceship yang bergerak tu. Adakah length of the spaceship yang bergerak tu akan sama panjang dia akan sama dengan masa dia at rest yang gambar nombor 1 tadi ke, ataupun dia akan memendek macam kata kawan kita dari KL tadi?
Saya rasa panjang dia punya leg sama, same. But walaupun pergerakan dia laju.
Okay. Nurul Ain memang dalam kumpulan yang kata length absolute tadi kan? Okay, tadi yang KL tadi Selvam Selvam dalam kumpulan yang kata that length is not absolute. Length boleh berubah bergantung kepada hal laju dia. Okay, now. So kiranya Nurul Ain. So now, apa yang you boleh nampak ni Nurul Ain? Apa yang boleh nampak?
Maknanya semakin laju dia punya leg akan mengurang.
Apa yang mengurang?
Saiz space tu mengurang bila kelajuan dia bertambah.
Okay, saiz tu apa?
Length, doktor.
Okay, length. Dia kat fizik ni kita kena cakap dia betul-betul apa dia kuantiti yang diukur. Okay, panjang dia kan? Okay, so katakan kalau pada 0.99C, jadi
length dia bertambah pendek.
Okay, kan? Jadi adakah panjang tu mutlak?
No.
Tidak kan? Jadi panjang tu boleh berubah bergantung kepada Jadi panjang sesuatu objek boleh berubah bergantung kepada
berubah bergantung pada kelajuan. Velocity.
Okey. So betul lah ya, satu kumpulan tadi kan yang kata panjang adalah tidak absolute, tidak mutlak, tapi ia bergantung kepada had laju. Okey. Jadi sekumpulan yang kata panjang tu mutlak, tolong perbetulkan konsep yang ada di dalam kepala tu. Okey. Sebab itu langkah pertama untuk you belajar tajuk ini. Okey. Kalau you dalam kepala you tak convinced that length do change with motion, then it's very difficult for you to learn this concept. Okey. Tolong perbetulkan yang dalam kepala ya. Ubahkan ya. Ni kalau kita nak tengok for the fun of it lah. Kan? Jadi kalau you tengok daripada this animation ya, apa dia 4 perkara yang you boleh cerap? Apa yang you boleh conclude daripada gambar ni? From this animation. Pertama,
the higher the speed, the shorter the length will be.
Okay. The higher the speed, the shorter the length will be. Okay, itu satu. Lagi? Dua?
It will become invisible if it reach the speed of 1.0 c.
1.0 c. Okey, mana dia boleh jadi invisible? Dia boleh ke sampai reach boleh ke dia sampai speed 1c? Objek tak boleh ya mencapai speed tak boleh mencapai had laju cahaya. Objek yang ada jisim tidak boleh mencapai had laju cahaya. Okey. Nanti kita akan belajar apa pasal dia tak boleh sampai had laju cahaya. Okey. Okey, itu tadi pendapat yang kita terima. Okey, jadi kita cuma boleh dah dapat satu kesimpulan saja. Ada lagi 3 kesimpulan yang kita boleh dapat daripada gambar ni. Apa dia? Senyap saja. Apa dia? Tadi faster means shorter. Okey, lagi? Shorter pada arah mana? Shorter pada arah mana?
Prof. Selvam from KL.
Yes.
It's shorter in the direction of the motion of the spaceship.
Okay. So kita nampak kan? Shorter the direction of motion. Okay, faster means shorter, tapi shorter in the direction of motion. Okay, apa lagi 2 lagi? Tadi kan kita kata something about length absolute ataupun tak absolute. Jadi conclusionnya adalah apa?
No, the length is not absolute.
Okay, the length is not absolute kan? Okay, now ada lagi satu. Macam mana? Kalau objek tu at rest, adakah panjang dia akan berubah ataupun tidak?
Maximum length.
Okey. So objek kalau ya dia di dalam rest frame dia, maka panjang dia tak berubah. Nurul Ain, do you understand what I'm saying now?
Yes, Prof. Dapat dah.
Okey. Kalau objek gerak, panjang dia tak akan berubah. But kalau pergerakan baru boleh berubah. Tapi kesannya kita cuma akan lihat kalau pergerakannya sangat laju. Itu sebabnya Nurul Ain kita biasa hari-hari kita tak nampak kan. Sebab pergerakan dia slow. Tapi kalau laju sangat-sangat baru kita boleh nampak. Okay, so apa dia 4 perkara tadi ni? 1.
Faster, shorter.
Faster, shorter. 2. Apanya? Tak dengar. 2. Come on.
In the direction of motion.
Okay, so shorter in the direction of motion. 3.
The higher the speed, the shorter the length will be.
Okay, tentu nombor 1 ni. Okay, nombor 3. Dah lupa dah soalan nombor pertama sidang video kita tadi.
Prove object never reach the speed of the light.
Itu cerita dalam simulation ni. Mana ada simulation ni at 1C, tak ada kan? Okay, apa dia? Nombor 3.
Object the rest will never change.
Okay, object rest length will never change. Yang motion saja change kan? Lagi satu?
Length is maximum when it's rest. Length is maximum when it is at rest.
Dia bukan length is maximum. Length is what it is at rest. Okay.
Yes.
Okay. Lagi satu tertinggal. Apa everybody? Apa dia?
Length is not absolute.
Length is not absolute. Jadi ada 4 perkara ya. Okay. 4 perkara. Okay, length is not absolute. Faster means shorter. Contraction is the direction of motion. And length of object in its rest frame does not change. Sebenarnya kan, you all understand ke apa maksud rest frame tu? Faham ke tidak apa maksud rest frame tu? Cuba beritahu saya sekejap.
Tak bergerak, kerangka dia tak bergerak.
Okay, kerangka dia tak bergerak. Okay, so kalau dalam cerita ini ada berapa frame? Ada berapa reference frame? Ni, dan case yang nombor 1 ni. 0C.
0C 1 je.
1.
Ngapa ada perkataan je tu?
Dengar.
Apa pasal you kata 1?
Sebab statik.
Okey, sebab dia statik kan. Okey, sama-sama kan? Sama-sama. Kan? Sama-sama tak gerak. Okey. Jadi kalaulah macam you all kat Penang tu kan. Jadi you all semua dalam satu rest frame. Adakah Penang, Melaka, Kota Baru, KL ni dalam satu frame ke tidak? Kita semua ni dalam satu frame ke tidak? Lekas jawab.
Ya.
Benda yang lambat lah.
Apa pasal ya? Apa pasal kata ya? Why do you say yes?
Sebab conference face to face dengan lecturer.
Lah pula. Adakah reference frame cerita dia face to face conference? Isu dia apa? Yang you all boleh kata kita ni sama rest frame. Sama frame.
Sebab kita tak bergerak.
Okey. So, kita tak gerak means walaupun di mana you all berada, kita share the same frame. Okey, boleh? Boleh ke? Faham ke? You all kau faham kata tak faham. Nanti kan saya tanya soalan banyak kali benda yang sama. Okey, faham ke? Okey. Dia macam ni. Dalam fizik ni, kalau you all faham kata faham. Kalau tak faham kata tak faham. Dan saya boleh explain. Kadang saya cakap seorang aja, you all macam balik dah bela. Tak guna kan? Tak mau bela-bela. Okey. So now, kalau kes 0.1C ni, ada berapa reference frame? 2. Okey. Kenapa 2?
Satu constant.
Ha? Kenapa 2? Kenapa 2? Tak cakaplah. Kenapa 2? Why? What makes you say ada 2 reference frame? Yang mana satu reference frame tu? Di mana? Where is it?
Orang.
Orang tu dengan orang tu satu reference frame. Lepas tu? Lagi satu kat mana?
Sheep.
Lagi satu dekat
Spaceship.
spaceship. Jadi dia ada 2 kan? Jadi satu orang kat bumi ni, satu lagi reference frame dekat spaceship. Okay. So now, reference frame mana yang at rest? Reference frame mana yang at rest?
Orang. Observer.
Okey, itu orang Penang kata. Ni orang Kota Baru? Okey, student Kota Baru? Siapa yang at rest?
Observer.
Observer.
Observer. Dengar tak?
Memanglah dengar. Okey, KL?
Frame 1. Yang pertama tu, gambar ajar pertama tu.
Yang mana tu? Oh, yang satu. No, saya
Yang
nak
atas sekali tu.
yang nombor 2. Yang at 0.1C spaceship moving at 0.1C tu. Siapa reference frame
Okey.
at rest?
Orang yang melambai-lambai tu.
Orang yang melambai-lambai tu. Okey. Okey, Melaka?
Yang melambai tu.
Oh, yang melambai-lambai
Observer.
tu. Oh, okey. Alright. Sebenarnya, ya, at rest tu, dia bergantung kepada siapa yang lihat. Pada yang melambai-lambai tu, dia nampak spaceship yang bergerak kan? Tapi orang dalam spaceship, dia akan nampak apa? Orang dalam spaceship akan nampak apa?
Orang dalam bergerak.
Siapa yang bergerak?
Orang yang di bawah bergerak.
Yes, orang yang di bawah bergerak. Jadi, siapa yang rest frame?
Spaceship person.
Pula. Tak pula. Lambai-lambai. Jadi, rest frame ni, dia bergantung kepada siapa yang melihat. Okey, pada orang spaceship, dia at rest. Pada yang orang melambai-lambai, dia at rest. Jadi, kiranya whether rest or not at rest adalah tak absolute kan? Okey. So you all kena fikir benda-benda macam ini tau. Sebab nanti bila kita nak solve problem nanti, kalau you bahagian ini you tak faham lagi, susah. Jadi rest or not at rest bergantung kepada siapa yang melihat. Okey, boleh? Alright. Okey, ada apa-apa soalan sebelum kita nak pergi ke brain teaser ni? Sebab kita tinggal 15 minit lagi ni. Kan? Okey, ada apa-apa soalan? Okey, tak ada. Saya akan bagi brain teaser ya. Yang ini akan jadi you all punya assignment video conference kedua. Okey. Okey, ini ada farmer. Ini farmer ya. Ini ban. Cakap Melayu apa ban saya pun tak tahulah. Kepuk lah, kepuk. Okey, panjang ban ini 10 meter. Okey. Panjang ban ni 10 meter. Ini ada orang lah ya. Dia berlari bawa satu kayu pole. Panjang pole ini 16 meter. Ya, soalan dia. Is it possible for the pole to fit in the bun? Kan? Soalan dia, adakah mungkin bagi apa nak kata kayu ni untuk cakap Melayu apa celui ya, cukup saja dia dalam ban yang panjang dia 10 meter ni. Is it possible for the pole to fit in the bun? Okay, so you all fikir. Saya bagi, okay, kita ikut pusat wilayah lah ya. Okay, Kota Baru, fikir among you all. And then, bagi fikir Melaka, fikir among Melaka. Saya bagi berapa minit lah? 7 minit untuk fikir. Penang, bincang antara you all, bincang. And then jawab soalan ini. You all jawab kat Padlet ikut pusat wilayah. Okay, bincang antara you all. Macam mana? Tak ada nampak macam bincang pun. Okay, saya bagi 7 minit. Okay, ada siapa-siapa nak cuba dulu? Pusat wilayah mana nak cuba dulu? Okay, pusat wilayah mana nak cuba? Okay, Penang nak cuba dulu. Okay, lekas Penang. Pusat wilayah mana nak cuba?
Selvam here.
Okay.
If the man can run fast enough, the pole will become shorter according to the theory of relativity. But then by the time he reach inside the bun, the pole will become at rest. So I don't think the pole can fit into the bun.
The pole will be at rest. Kenapa the pole will be at rest?
Dia dah masuk dalam ban tu, dia kena stop kan? Dia kena berhenti kan?
Katakanlah ban tu ada pintu depan dengan pintu belakang.
In that case, it is possible. Because if he can run fast, but the problem is, I don't know whether he can run that fast or not.
Okay. Itu pendapat Selvam. Okay. Itu pendapat Selvam. Okay, what about dari Penang?
Prof, possible, Prof.
Okay. Okay, possible.
No, it's not possible.
Oh,
The pole might look shorter.
Itu daripada Kota Baru. Okay.
Khairul Hadi daripada Kota Baru. No, it's not possible. The pole might look shorter on the ice, but the actual length of the pole won't change. So it won't fit lah.
Okay, ice apa tu?
Observer. It might look shorter. The observer might look to the pole as shorter than the actual length, but actually it's not. It's only look shorter is on his vision.
Oh, pada vision dia saja look shorter, tapi actually it's not shorter.
Yes.
Siapa observer tu? Who's the observer? Dalam kes ni siapa observer?
The farmer.
Oh, jadi kiranya benda ni is something trick of the eye lah ya. Something silap pada mata.
Ya.
Silap mata.
Oh. Pada you
Spaceship
all,
tadi.
benda ni something silap mata kita tengok ya. Bukan benda tu sebenarnya kontrak, bukan. Is it?
Yes.
Yang tadi simulation yang saya tunjuk tadi tu, itu silap pada mata ya. Bukan sebenarnya benda tu kontrak.
I think so.
First time saya mengajar benda ni dah 30 tahun ya. Orang tu kata silap pada mata ya. Bukan realitinya benda tu kontrak. Betul ke saya cakap ni? Realitinya kontrak? Realiti tu siapa yang realiti, isn't it? Kalau pole tu pada orang lari tu, adakah panjang tu akan berubah?
Panjang tak berubah, bro.
Sebab apa tak berubah? Kenapa you kata dia tak berubah?
Dia punya
Panjang tetap panjang.
Pula. Sebab panjang tetap panjang.
Panjang pun tetap panjang. Yang bila orang yang bawa pool tu lari, yang farmer tu tak dapat mengagak kepanjangan sebenar pool tu. So dia assume, yang farmer tu assume yang runner yang bawa lumpur tu muat untuk masuk dalam ban. Yang itu kalau misal kata daripada mata farmer, memanglah benda tu possible untuk masuk. Tapi pada hakikatnya benda tu tak muat. Tak lepas.
Saya lagi berpendapat bahawa panjang mutlak. Panjang is absolute. Sebab you ada pada hakikatnya, macam pada realitinya panjang tu tak berubah.
Kalau spaceship macam tadi, panjang dia berubah. Kalau yang sebenar actual dia berubah. Macam mana orang kat dalam tu boleh bernafas, boleh muat kat dalam tu?
Pula. So, jadi macam mana you nak reason out pada diri you sendiri apa yang you tengok tadi?
Logiknya nampak kat mata je lah macam tu, tapi sebenarnya tak.
Nampak kat mata. Mata siapa?
Observer lah, siapa yang melihat.
Sebenarnya tak tu apa?
Sebenarnya kalau spaceship tadi, macam spaceship tu, nampak macam dia menjadi pendek kan. Tapi sebenarnya tak. Sebenarnya panjang dia, length dia samanya. Orang kat dalam tu tak sesak nafas pun duduk dalam tu.
No, you ulang balik apa you cakap tadi ni?
Macam ni panjang spaceship tu kat mata je menjadi pendek.
Wait.
Kan?
Nampak
orang kat dalam spaceship pada pandangan mata, maknanya yang observe tu dari pandangan mata. Kalau contohnya bukan mata yang melihat macam mana, dia benda tu tetap sama sebenarnya, cuma pandangan mata je. Sebab orang kat dalam tu, dia kat dalam spaceship tu tak berubah pun space dalam spaceship dia tu, ruang dalam spaceship dia tu tak akan berubah macam mana pun. Tapi ini cuma di pandangan mata saja.
Di pandangan mata saja. Sebenarnya apa you cakap tu tak berapa betul, sebab kejadian tu memang benda tu kontrak.
Memang benda tu mengecil lah. Memendek.
Yes. Sebab itulah sebab benda ni dia berlaku pada reference frame yang berlainan. Memang dia berlaku benda tu macam itu. Dia memendek. Kalau
secara logik, kalau memendek, habis tu kenapa tak berubah pun orang kat dalam tu? Dalam spaceship.
Itu sebabnya kita ni cerita orang di dua rangka rujukan yang berbeza.
Yelah, bagi saya itu cuma pandangan nampak saja macam tu. Tapi sebenarnya tak.
No. Dia macam ni. Orang yang dalam rest frame benda itu, dia tak berubah. Tapi orang yang tengok benda tu memang berubah. Kalau you ukur, dia memang ubah. Jadi dia bukan pada pandangan mata, bukan. Dia disebabkan oleh you nak mengukur, you mengguna cahaya untuk mengukur. Sebab benda tu memang mengecil pada rangka rujukan orang ni. Tapi pada rangka rujukan orang tu memang tak berubah. Benda-benda ni memang berlaku.
Maknanya kalau contohnya balon udara tu naik, dia daripada bawah besar, bila naik dia makin kecil kita tengoknya. Tu adalah daripada sudut pandangan mata, vision dia tu, ataupun memang mengecil betul.
Dia macam ni, itu isu lain, itu isu perspektif. Benda ni bukan isu perspektif. Memang kita nampak dia makin jauh sebab perspektif kita. Tapi kalau benda tu memang bergerak laju, memang dia mengecil. Pada pandangan kita tengok dia memang kecil. Tapi pada rangka rujukan dia memang tak berubah dia punya saiz. Jangan confuse dari sudut perspektif dengan perbezaan rangka rujukan yang bergerak laju.
Saya rasa saya boleh terima yang pasal perspektif tu lah. Cuma yang pasal ni masih confuse lagi lah. Puan.
Oh, masih confuse lagi. Dia sebab dia kalau pergerakan dia memang susah nak tunjuk. Tapi kalau macam masa, senang nak tunjuk. Katakanlah kita sebut daripada aspek masa. Mungkin aspek masa senang untuk saya terangkan. Tapi kalau panjang ni, actually okey je sebenarnya. Tapi takut you all susah nak terima. Okey, kalau daripada aspek masa kan. Kan masa, kalau kita bergerak laju, then apa berlaku pada masa, detik masa tu? Kalau kita bergerak laju, maka detik masa
slower.
Kita akan slower kan. Kalau detik masa slower, kiranya denyutan jantung kita ni get slower, then apa yang katalah kita ada dua twin. Satu twin duduk kat bumi. Satu twin dia bergerak menghampiri had laju cahaya. Okey. Jadi twin tu bila dia balik Malaysia, dia jumpa dengan twin dia yang tinggal tu. Siapa lebih muda ataupun sama age?
Younger.
Siapa?
Younger.
The one who travel.
The one who travel at the speed of light will be younger, isn't it? Apa pasal younger?
Because of the heartbeat slower.
Yes. Katakanlah ada dua twin ni, satu twin kuroi, satu twin gemuk. Jadi twin gemuk ni pergi to the speed of light, near the speed of light. So twin yang kuroi ni bila dia tengok twin yang gemuk tu, jadi apa dia akan nampak?
Memang dia akan nampak yang gemuk tu jadi kurus. Tapi kalau dia aja cuma pandangan mata je kot.
Kalau apa?
Cuma di pandangan mata lah, bila dia bergerak dengan laju, dia akan jadi kurus macam yang kurus orang lagi tu. Tapi yang sebenarnya bila yang gemuk tu berhenti, saiz dia tetap sama.
Yelah, kalau dia berhenti memang dia tak berubah lah. Betul lah tu. Tapi bila dia bergerak tu memang dia akan nampak slimmer. Jadi bila kita tengok because of rangka rujukan yang berbeza, and also dia bergerak, and because cahaya, kelajuan cahaya tak berubah. It is always constant dalam vacuum. Okey, tak apa. Saya akan letakkan soalan ini dalam portal. Nanti you all tolong jawab ya. Tapi the thing is, jangan jawab macam rupa yes or no saja. Tapi bagi bukti untuk menunjukkan benda ni possible atau tak possible. Jadi gunakanlah ya rumus-rumus yang tertentu untuk menunjukkannya. Okay. Sorry, masa dah cukup. So, kita bergerak ke portal lah ya. Nanti kalau apa-apa soalan, saya akan upload ni sebentar lagi ke? Malam inilah saya upload ya, soalan ini. So, kita akhiri kita punya video conference sekarang. And thank you for you all punya participation. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Okay, so today is going to be our third video conference for JIF103 Physics 1. As I've stated in the academic planner, so this video conference will talk about relativity of simultaneity. Actually, simultaneity is one of the aspects that comes from Einstein postulate. That is, all speed of light is the same in vacuum, and also all physics laws are equivalent. Okay, so it derives from there. This topic is not covered in your textbook. So make sure you understand from this video conference what it meant about simultaneity. Ataupun dalam bahasa Malaysia, keserentakan ya. Okay, so let's see who's who. So we have several of our friends in Kuala Lumpur. And then we have, please introduce yourself so that I can call you up.
Hafizul from Kota Baru.
Okay, Kota Baru, Hafizul. And then?
Good morning, Hafiz from Alusta.
Hafizul, KB, Alusta, Hafiz. Who else? No name from KL. Yes.
Hello, Azizul
Yes.
from KL.
Why don't all of you from KL sit next to the table rather than you walking every time? Okay, so as I've told you just now, make sure you understand properly what it meant by simultaneity because the textbook doesn't cover it, But this is the manifestation of the Einstein 2 postulate, how it changes our space-time, Okay, basically what we are going to talk today is about 4 issues. First, I am going to introduce to you what is meant by the time of an event. Okay, what is meant by the time of an event. Next, what is meant by simultaneous. So that your understanding and my understanding are the same, Are 2 events simultaneous to 2 observers in the same reference frame? And the last one is, are 2 events that are simultaneous to an observer are also simultaneous to another observer moving relative to him? So these are 4 issues, Because basically, in order to know this third and fourth issue, you need to understand what it means by simultaneous and what it means by an event. Okay, as usual, let us define what is the time T of an event. Okay, let's say there's a person A who stands at 0 meter, at the position 0 meter, and another person B standing at the position 900 meters away from person A. Okay. And at 600 meters, there's an explosion, a firecracker explodes. Let's say it happens at time T is equals to 0. The speed of light speed of light travels 300 meters in 1 microsecond. So if you look here, how long, what's the time for it to reach B? So what is the time for the light from the explosion to reach B? So T will be equal to, Hafiz. So T will be equal to?
T equal 3 seconds.
Wait, 300 meters in 1 microsecond. So the distance between this one is and this one is 300 meters. Then T will be, so T will be speed or light will travel 300 meters in 1 microsecond. So the distance between the explosion and person B is 300 meters. So T will be, for person B, the time that he will see the explosion will be, so T will be 1 microsecond, isn't it? Because the distance here and here is 300 meters. So the wavefront from explosion will reach B after 1 microsecond. And to reach A, it will be 2 microseconds because the distance from A to the explosion is 600 meters. Okay, do you all agree with this? Okay, do you understand how I get 2 micrometers and 1 microsecond and 2 microseconds? Do you get it? Yes or no?
Yes.
Okay, so now, what is the time of the explosion? Is it T is equals to 2 microsecond? Or is it T is equals to 1 microsecond? Or T is equals to 0?
0.
So T is equals to 0. Yang itu dari mana tu? KL? Okay, what about the rest? Okay, one of our friends say the time of the explosion is T is equals to 0. Okay, do you all agree with it? Yes? Anyone? So everybody agrees with it? Okay, so the time of an event is the time when the event actually happened. So just like what our friend said, yes, the time of explosion is T is equals to 0. So it's not the time when the event is seen. Yeah. So even though B see the explosion at T is equals to 1 microsecond, but the time of event is when the explosion happens. Okay. So the time of an event is when the event actually happened and not the time when the event is seen. Okay, semua orang get it?
Yes.
Okay, great. Now, let's say, okay, so this is the hydrogen cloud formation after Big Bang. You see it now. So, the time of event is 3 billion years ago. So, what you see now is not the time of the event, isn't it? The event of hydrogen cloud formation. Even though you see it now, but actually the event happens 3 billion years ago. So this is an example to show that what you see now is not necessarily the time of the event. Okay. Okay. So I stress now, because we are going into what it meant to be simultaneous or not, you need to be sure, what it means by the time of the event. Okay, so everyone that agree, time of event is when it actually happens. Now we go to the next term that you need to know. What is meant by simultaneous? Apakah yang dimaksudkan dengan keserentakan? Okay, let's say we have one tree at position x1 and another tree at position x2. Let's say two lightning strikes these trees. Let's say the lightning strike tree 1, it says event 1, and lightning strike tree 2, we say is at event 2 at t is equals to at t2. If t1 is equals to t2, and we know that x1 is not equals to x2 because different position, one at this place and another at the other place. Ready? Simultaneous means two events, event 1 and event 2 at two different position, but occurs at the same time. Keserentakan ditakrifkan sebagai apabila dua peristiwa yang terletak di tempat yang berlainan tapi berlaku pada masa yang sama. Simultaneous means the two events must occur at the same time, but those two events must be at different positions. Okay. Did you get what it means by simultaneous?
Yes, Prof.
Okay, great. Now, let's go to our first brain teaser. Okay, remember what is meant by an event and also what is meant by simultaneous. Okay, now, let's go to our first brain teaser. Okay, let's say there's two explosions, the explosion occurs at 600, the position 600 meter, and then another explosion occurs at 1,200 meters. Okay. Okay, explosion 1 and explosion 2. So the question is, okay, let's have the situation. Wavefront 1 reaches A at t is equals to 3 microseconds, and explosion 2 reaches A at t is equals to 5 microseconds. So the question is, are the two explosions simultaneous to A?
Yes.
Okay, yes, kata di kawan kita. How do you know it's yes? Why do you say yes?
Sorry, no.
Sorry pula dah. Kenapa? Okay, why do you say yes? No. The one thing about physics is not just know the answer, but you have to have the reason why you come up with such answers. Okay, why then? Why do you say it's simultaneous? Remember, speed of light 300 meters in 1 microsecond, and like we have talked before, time of event is time when the event actually happened and not the time when the event is seen. So based on these two hints, what can you say? How can you use these two hints to solve this question? Okay, siapa yang mic off kan because they are humming? Okay, anyone in KL? What is your opinion? Our friend in Nibong Tebal that would like to try to answer. Come on. We are here early in the morning. Let's have some good discussion. Okay. Anyone? Come on.
Prof.
Yes.
Simultaneous.
Simultaneous. Okay.
Because it happened in different position.
Because it happens in different position. Is that the only condition? Apa tadi dua condition untuk simultaneous?
At the same time.
Okay, the same time. How can you prove that it is at the same time? Macam mana to show? So macam mana to show that it occurs at the same time? Okay, kawan kita from KL. Yes.
Good morning, Prof.
Yes.
It's not very clear here with the first one. Is it 3 or 2?
3 microsecond. The first
The
one.
second one is
5 microsecond. 5.
okay, but if the speed of light is 300 meter in 1 microsecond,
Yes.
and the distance is 600 meter,
Yes.
how come there's a 3 microsecond there? It should be 2, right?
Why you said it should be 2?
Are we using the speed of light for the
Yes.
person to realize
Yes.
the event happened?
Yes.
So if it's 600 meter, if one microsecond the speed travel 300 meters, so for 600 meter it will travel 2 microseconds.
Okay.
But
Okay,
what I
right.
see here is written there 3 microseconds. So I'm checking whether the numbers are actually correct or is there any mistake.
The number is correct. So it means the time of explosion 1 is t is equals to
T equals to
t is equals to, yes, you are right. Okay, there's something in your mind. So t, the time of explosion 1 is at t is equals to, because in your mind you said you think that t is equals to 0 at explosion 1, isn't it?
yes.
Yes,
T equals 0. Right?
No. It won't be
It's supposed to reach in 2 microseconds.
Oh? Because we know that it reaches at t is equals to 3 microseconds. So
Yes.
time of
It's supposed to reach in. Yeah, it's supposed to reach in 2 microseconds, but it reach in 3 microseconds. That means the action are not simultaneous.
not simultaneous pula dah. But how do you prove that it is not simultaneous? Simultaneous, first, it must have a different position. Like our friend in Nibong Tebal say, yes, indeed. But what about the time? The time of explosion explosion 1 and the time of explosion T2, explosion 2. What about their time?
Masuk.
So it takes 2 microseconds, isn't it?
Yes.
What you said. Okay,
Yes.
now then T1 is actually what?
Itu dia tanya.
T2 dia tanya T1.
T1 tu?
T1 is 2 microsecond. T2 is 4 microsecond.
Oh lah.
Okay, why do you say it's 4 microsecond? Macam mana tu? So, if this one is 2 microsecond, the time it takes for explosion 1 to reach A, but this one is 3 microsecond, then T1 should be, it's not at T is equals to 0, isn't it? So it will be at T1 is 1 microsecond. What about at T2? For T2, it takes 4 microseconds to reach A. So T2 is 5 minus 4 is equals to 1 microsecond. So now, calculator from nibung tebal, we can see now is T1 and T2 is the same, isn't it? The time of the event. So the two explosions are simultaneous. Okay. Ya, kawan kita from KL just now, because you thought that this one is T is equals to 0 microsecond. But now, it's not. T1 is equals to 2, because we knew that this one is T is equals to 3 microsecond. So, tolak 2, so we get 1 microsecond. Bolehkah? Did you get what I'm trying to tell you? Bolehkah?
Assalamualaikum.
Waalaikumsalam.
Doktor, tak faham.
Tak faham. Okey, tang mana yang tak faham tu, Ainul?
Kenapa kena tolak?
Kenapa kena tolak? Sebab kita nak tahu masa dia. Masa event tu berlaku. Sebab kita tahu one reaches A at 3 microsecond. At T is equals to 3 microsecond. Okay? Kat sini 3 microsecond. Jadi, masa yang diambil 2 microsecond. Jadi, benda mestilah berlaku at 1 microsecond. Sebab kita nak tahu what is the time of the event. Yang ketika wave ni sampai dekat A, 3 microsecond. Masa yang diambil untuk sampai ke A, 2. Jadi benda tu mestilah berlaku 1 microsecond lah kan. Pada T is equal to 1 microsecond. Kalau nak tengok satu cara lain, ketika time is equal to 1 microsecond, benda ni berlaku. Kemudian dia mengambil masa 2 microsecond nak sampai ke A. Itu sebab bila sampai ke A, dia 3 microsecond. Okay, boleh Ainul? Nampak tak? Okay, boleh ke?
Doktor.
Ya.
Maknanya event tu berlaku pada 3 microsecond lah?
No. Event berlaku 1 microsecond. Dia A nampak ketika T is equal to 3 microsecond. A nampak explosion tu pada masa T is equal to 3 microsecond. Tapi event explosion tu pada masa T is equal to 3 microsecond. Tapi event sebenarnya berlaku satu pada masa T 1 microsecond. Sebab cahaya mengambil masa untuk sampai ke mata kita. Okay, time of event adalah masa benda tu berlaku, bukan masa benda tu sampai ke kita. Okay, Ainul? Okay, boleh? Okay. Faham tak benda ni? Isu ni? Kalau dah faham, saya nak bagi lagi satu brain teaser dan cuba. Did you get ni? Faham tak ini? Ke tak faham?
Yes.
Faham ke konsep ni? Okey, faham dah kan konsep ni? Okey, simultaneous adalah dua event tu mesti terletak pada tempat yang berlainan, tapi masa dia berlaku mestilah sama. Okey. Now, saya bagi lagi satu brain teaser. Okey. Ya, sama ya. Dua explosion dekat 600 meter dengan 1200 meter. Now, explosion 1 and explosion 2. Katakanlah ya, wave front ya, A nampak explosion 1 ini pada masa T is equals to 5 microsecond. Kemudian dia nampak juga explosion 2 berlaku pada masa dia nampak ya benda ni pada masa T is equals to 5 microsecond. Ya, kedua-duanya dia nampak pada masa yang sama. Okey. Are the two explosions simultaneous? Okay, so tu soalan dia. Are the two explosions simultaneous? Okay, macam mana tu? Okay, siapa boleh jawab betul semua, saya bagi markah.
Finik.
Selvam from KL.
Okay.
Good morning, Prof.
Yes.
Yes.
Apa nama you tadi? Kan saya lupa.
Selvam.
Selvam.
Selvam from KL.
Selvam. Okay, Selvam.
The two explosions are not simultaneous.
Okay, sebab?
The reason because the explosion one happened at 1 microsecond. Sorry, not 3 microseconds. And explosion 2 happened at 1 microsecond.
Okay. How do you get that 2 and 1 microsecond?
Explosion 1 happened at 3 microseconds, and explosion 2 happened at 1 microsecond.
How do you
So
get that?
Okay, 600 meter minus 0 is 600 meter divide 300, I get 2 microseconds.
Okay, yes.
But the explosion reached A at 5 microseconds.
Okay.
So 5 minus 2, I get 3.
Okay, correct, yes.
Okay, the second explosion, 200 meter divide 300, I get 4 microseconds. But the wave reached A at 5 microseconds.
Okay.
So 5 minus 4, I get 1 microsecond.
Okay, that's right, Salva. So,
Okay, thank you.
got it. Yes. I'll make sure. Yay. 5 marks to Salva. Okay. Alright. Okay, so it seems, did all of you understand what Salva said just now?
Yes.
Okay, tak apa. Ada banyak lagi soalan. Don't worry. Still time. Okay, now that's brain teaser number 2. So it's about simultaneity, yes. Sama ada sesuatu benda tu simultaneous ataupun tidak, ya. It must happen at the same time, ya. But the two event must be at two different position. Okay. So ni two different time, ya, like Sevan explained just now. Ya, T1 3 microsecond because the wavefront reaches it at 5 microsecond, but it takes 2 microsecond for the wavefront to reach A. So the time of the explosion is 3 microsecond, and of course for explosion 2 is 1 microsecond. Alright. Now let's try another one, yeah. Okay. So let's say this is mud, yeah. Mud is sitting between two trees, yeah. Midway between two trees, yeah. He saw two lightning bolts at the same time, at the same instant of time. Are the two lightning bolts simultaneous in Mud's case?
Yes, bro.
Okay. Tu siapa tu? Ainul. Okay. Kenapa? Why? Why you say so, Ainul?
Because the distance mud is same, so the explosion have the lightning strike the tree is same like a second. It's why.
Okay, so to mark the both lightning strike at the same time, and since the distance is the same, so between these two, between him, then it's simultaneous. Okay, now what about Ali? Let's say Ali 6 under 3 on the left. In Ali's case, does the two lightning bolt simultaneous? Yeah.
No, bro.
Okay. No. Cepat saja dapat mendu. Why do you say no?
One is yes, one is no.
Udah. Yang mana satu tu? Ali punya case yes or no? Simultaneous ataupun
No.
tidak?
No simultaneous.
No simultaneous. Why? Why do you say no simultaneous?
Because the lighting happen with Ali is 0 meter. The second one is 600 meter. So the time curve will be different.
Time of apa final? Time dia nampak ke?
Time apa ni?
Time dia nampak will be different ke? Time of event will be different.
Prof, time dia nampak, Prof.
Then tapi time of event?
Event
time
sama.
of event sama.
So
masa time Ali nampak, the time is 0, and then masa then Ali nampak dekat another tree, the time is 2 millisecond.
So simultaneous ke tidak in Ali's case?
No, it's not simultaneous. Because it's a different distance between of the trees.
No. Time of event apa dia? Time of event, time dia nampak ke? Time apa?
The time Ali sees the lightning at the other tree is 2 milliseconds. So means that this is a time of event. This is a time Ali seen. The times the times of the events sama saja antara tempat Ali and another tree. But tempat Ali nampak tu the time is 0. The other trees the time is millisecond. So Ali akan nampak dulu kat tempat dia, and then after that baru dia akan nampak another tree pula.
Betul tu. Tapi adakah dua lightning bolt ni simultaneous pada Ali?
No, it's not simultaneous.
Okay, tu Ainul. Yang lain?
No, it's me, Nabila from Alustar.
Oh, okay, Nabila from Alustar. Okay. So Nabila kata bukan. Tapi isu dia simultaneous ni kita guna time nampak ke atau time of the event?
Based on the questions in Ali's case, but question ni tanya in Ali's case. Means that kan masa Ali nampak.
Bukan.
Bukan.
No, macam ni. Kita nak tengok simultaneous ataupun tidak, dia ada dua condition kan? Satu, benda tu mesti berlaku pada tempat yang berlainan. Condition yang kedua apa? Condition yang kedua? Apa? Dia mestilah sama.
Time
apa yang mesti sama?
Time of event.
Adakah sama time of event dengan time of nampak?
Tak.
Okay, so dalam kes ini dalam kes Ali
Tak sama.
Sama sebab dua microsecond.
Kenapa tak sama?
Oh, sama ke? Sama.
No, simultaneous ni kita guna time nampak ke time of event? Balik semula. Okay. Kita consider simultaneous apa? Position mesti berlainan and then time of event mesti
Sama.
Okey, ni dalam kes Ali, time of event dia sama tak sama?
Sama.
Sama. Jadi
Simultaneous.
yes, simultaneous lah. Nabila, okey ke?
Okey puan, saya terbalik.
Okey. Terbalik tu kat mana yang terbalik tu?
Saya terbalik in terms of simultaneous and not simultaneous. And then sekarang faham lah the terms of the simultaneous.
Okey, great. Itulah dia. Terima kasih. Happy saya lah. Okey, now kita pula pergi isu ya. Jadi dua event will be simultaneous to dua observer sharing the same reference frame. Kan? Ali dengan Mat ni kan? Mana dia saya punya ni? Okay, so ini Ali, ini Mat. Dia orang share the same reference frame kan? Jadi, kalau these two observers share the same reference frame, kalau orang ni nampak benda tu simultaneous, the other person pun akan nampak benda tu sebagai simultaneous. Okay, boleh? Boleh, itu di conclusion yang kita boleh dapat daripada sini. Kalau dia share the same reference frame, satu person nampak benda tu simultaneous, the other one pun akan nampak benda tu simultaneous. Okay, boleh? Boleh ke? Semua orang setuju ke dengan apa yang saya cakap ni? You all buat sendiri just now kan? Nampak kan? Okay. Now, mari kita tukar kes pula. Adakah simultaneity ni absolute? Adakah keserentakan tu mutlak? Jadi, bila benda tu kita nampak serentak, adakah dia sentiasa akan nampak serentak?
Ya, doktor.
Ya. Oh, ya ke jawapannya? Ya kak? Okey. Pak. Sabar nak.
Oh.
Okey, katalah kita ada satu person, dia duduk kat sini. Ya, dia duduk kat reference frame yang address. Kemudian ada dua explosion berlaku ya at the same time ya, pada masa yang sama. Jadi pada orang ni benda ni simultaneous. Tapi soalannya, adakah apabila seorang ni dia dalam reference frame yang bergerak, bila dia tengok these two events ni, adakah pada dia simultaneous juga? Macam mana tu? You all rasa pada orang ni yang bergerak ni, let's say orang ni dalam kereta lah bergerak ya, adakah dia nampak dua event ni serentak juga ke?
No.
No? Cik Raju je no. Ya ke? Okay, so isu dia.
Dia daripada situ kan?
Nantilah. Okay, two events occurring simultaneously to an observer in reference frame S are also simultaneous to another observer in reference frame S prime moving relative to S. Adakah? Kalau ya jawapannya, then simultaneity absolute. Kalau no, maka simultaneity ni tak mutlak. Ya, kadang-kadang dia boleh berlaku serentak pada orang dalam frame ini, tapi pada orang frame ini tak semestinya. Okay, apa opinion you all? What do you all think?
Not absolute.
Oh, not absolute. Okay. Apa yang menyebabkan you kata demikian? Apa? Intuition saja ya, kata. Okay. Now, saya nak tunjuk simulation ya. You all tengok sendiri, then you tell me. Ya. Mari kita tengok simulation. Mana simulation saya ni? Okay. Okay. You all nanti boleh, nanti saya akan upload website untuk this simulation supaya you all boleh tengok by yourself. Yeah, in this series of simulation, we will show the existence of simultaneity of two events that depend on the frame of reference from which the events are observed.
Doktor, PowerPoint tak nampak.
Tak nampak? Dia bukan power. Oh, tak nampak dia screen.
Dia tak clear. Screen dia, tulisan dia kecil sangat.
Memang tulisan dia kecil. Itu sebab saya bacakan untuk you all. Okay, tak apa. Don't worry about that. Okay, nampak dah ada dua circle ni? Nampak dah dua circle?
Nampak.
Okay, dua circle ni simultaneous ataupun tidak? Nampak kan?
Nampak.
Simultaneous ataupun tidak?
Simultaneous.
Okay, alright. Betul lah tu. Okay. Apa? Konon ni, ini detector lah ya. Detector akan menyala apabila wavefront tu sampai pada dia. Okay, nampak kan? Sebab dia simultaneous, jadi detector akan menyala pada masa yang sama. Okey, boleh? Nampak? Nampak ke?
Okey, Prof. Nampak.
Okey, great. Okey, now, katalah benda ni satu berlaku dahulu, satu berlaku kemudian, tak simultaneous. Jadi, you akan nampak flash pada masa yang berlainan kan? Nampak tak?
Nampak.
Okey. Now, okey, kita dah tengok dah tadi. Jadi, now, kita ni nak tengok dua kes. Daripada sudut kereta api dengan daripada sudut platform. Kereta api ni, kalau depan dia kena pada hujung platform belah kanan, maka cahaya merah akan keluar. Okey, nampak tak? Nampak? Okey, now. Kalau belakang dia terkena platform, hujung platform, cahaya biru akan terkeluar. Nampak kan?
Okey.
Okey, now. So, ini kita nak tengok keserentakan dia. Okey, kita daripada platform tengok ke kereta api. Jadi, apa you all nampak? Muncung kereta api dengan belakang kereta api, dua event tu berlaku simultaneous ataupun tidak?
Simultaneous.
Okey, simultaneous ya. Ini kita lihat pada kereta api.
Mana kereta api?
Okey, tak apa. Tengok pula puan. Jadi, event muncung kereta api bertemu dengan platform, dengan belakang kereta api bertemu dengan platform pada masa yang sama kan?
Yes.
Okay, the two event is simultaneous kan?
Yes.
Tengok betul-betul. Baik. Okay. Agree kan? Everybody agree?
Agree.
Okay.
Tidak.
Tak. Okay, now kita nak tengok daripada perspektif orang dalam kereta api pula. Adakah orang dalam kereta api nampak benda tu simultaneous? Okay, now kita tengok pula ya. So, ini kita tengok daripada orang dalam kereta api ya. Orang dalam kereta api nampak benda tu simultaneous ataupun tidak?
Tidak. Tidak.
So like platform yang kontrol.
Jadi apa conclusion kita?
is not simultaneous.
Okay.
Simultaneity not absolute.
Simultaneous tak? Betul lah tu. Jadi isu dia dua event yang simultaneous in the ground reference frame daripada platform, tapi tak simultaneous dalam train reference frame kan?
Yeah.
So simultaneous is not absolute.
Sama Indonesia frame. Indonesia frame kita. Allah.
Okay, masa dah cukup. The next class. So apa yang kita dah belajar hari ni? Apa yang kita dah belajar hari ni? Let's conclude. Kita dah belajar hari ni. Okay, simultaneity is not absolute. Time of event, apa dia?
When event actually happens.
An event actually happens. Betul lagi?
Two event happen in different position at the same time is simultaneous.
Okay, great. Itu je lah ya kita belajar hari ni. Simultaneous tak absolute kalau dilihat daripada dua reference frame yang berlainan. Kalau reference frame yang sama, simultaneous tetap simultaneous kan? So itulah dianya yang kita belajar hari ni. So insyaAllah jumpa lagi masa kursus intensif lah dah. So as I've stated in our portal that we are going to discuss about your...
Hello, Assalamualaikum Prof.
Yes.
Prof, dekat Penang dia punya video tak ada. Kami tak nampak apa pun. Kami dengar suara je.
Oh ya ke?
Ya.
Macam mana tu Saya panggil Muzaffar ke dia boleh tolong selesaikan because this is dia kata dia tak nampak video.
Tak ada langsung, kosong je.
Memanglah kosong. Ni nampak tangan saya, nampak tak?
Itu dokumen kamera.
Tangan pun tak nampak, apa pun tak nampak.
Memang saya guna dokumen kamera.
Kota baru nampak tak?
Tak ada. Tak nampak.
Kota baru nampak? Kota baru? Kota baru.
Kota baru nampak jelas itu dokumen kamera, bukan video.
Memang betul dokumen kamera.
Okay, terima kasih.
Tak apa, dia pergi tengok dalam.
Okey, tak apa. Dia kat Penang, Encik Muzaffar nak pergi tengok kat you all tu. Okay, anyway, since I've stated in the portal that we are going to discuss about our continuous exam, so I have the exam question in front of me right now. I hope you do have your exam question with you also. So I can see there's only 2 students in Penang, is it? Okay, who's there in Penang then? Angkat saja that microphone near to you. And you don't have to walk. Okay, who do we have there in Penang?
Ya Prof, nama saya Nur Sabaria dan Tanah Lachmi.
Nur Sabaria and
Tanah Lachmi.
Tanah Lachmi. Okay, Tanah and Sabaria. So, now let's go to our first question here because I've marked all of your continuous exam scripts. The highest mark is surprisingly is 96. The lowest is 0. And I'm pleased because I think Einstein will also be pleased because there's new inventions to his ideas. Okay, let's go to the first question. With appropriate illustration, equation if any, Give your comments on the truthfulness of the following statements. Okay, the first one, yeah. Adam, Idris, and Noah are triplets. It is impossible for them to be of different ages. So how are you going to answer this kind of question, Sabaria? So what did you answer? How do you answer during the exam? So the first thing that should come into your mind is, so this is about what? Yes, Sabaria. So this is about
Twin paradox.
So it's about twin paradox. So basically twin paradox tu is about apa dia? Apa dia cerita dalam twin paradox tu? So apa dia? Okay, first of all, ya, adakah statement ini true or false? Dia kata it's impossible for them to be of different ages. So
It's true.
oh, it's true. Why do you say it's true? Sebab dia kata, give your comments on the truthfulness. Comment. Okay, you kata it's true. Why is it true? Apa dia supporting evidence that support you punya argument? Yes, it seems that there's several of our friends in Kuantan. So, do you want to answer? Okay, come on. Your microphone is on. Why don't you sit next to the microphone so that it's easier for you to answer? Come on, don't waste our time. Yeah? Is it impossible? Annoying twin paradox then? Or what is the basic concept behind twin paradox? It's about what? Time dilation, isn't it? So the answer is false, isn't it? Yeah, it's possible to have them at different ages. It is possible for them to have different ages. Yeah, how? Yeah, how different age? How? It has something to do with time dilation, isn't it? Time dilation says moving clock runs slower. So meaning we will age slower. Kita tahu apa dia relationship dia untuk time dilation ni? Time dilation T is equals to gamma T0, isn't it? So, it's equals to T0 bahagi divide by 1 minus V over C squared. So, what we can see now is time. Tengok kan faktor ini. Yeah, time do change with speed, isn't it? Kan? So, kita tahu bahawa the faster they go, macam mana? The faster they go, the more the time dilated, kan? P faster, then we have more kan? So, therefore, if Adam stays on earth, Adam stays, say Adam in the rest frame, v is equals to 0. And then, let's say Idris moves at v is equals to 0.5c. And then if we have no moves at 0.9c, jadi we can get different time, isn't it? So each will move at different v. So we get T0 untuk Idris more than T0 untuk Adam, untuk no. And T Adam. So T Adam is more than T0 Idris is greater than T0 no. Katakanlah ya, T Adam berapa? Let's say we say Adam 10 tahun. Ya, 10 tahun penambahan tahun dia. Tapi kalau Idris penambahan dia will be T0 is equals to 10 square root of, tak muat pula dah, 10 1 minus 0.5 squared. So kita dapat yang ini is about 8.7 years. Kalau no punya is equals to 10 square root of 1 minus 0.9 squared. So kita dapat this one is about 4.6 years. So kita tengok ya, masa dia, katalah Adam 10 tahun, katalah before they go anywhere, ya, their age is Adam punya age, Idris and no, katalah at t is equals to 0 ya, initial, at initial, katalah dia orang punya age is equals to 30 years. Ya. Jadi kalau tambah 10 years, Adam punya age will be around 40 years. Ya, Idris will be 30 plus 8 is equals to 38.7 years. Because apa? 30 plus 8.7. And untuk no, dia akan dapat 30 plus 4.6 is equals to 34.6 years. So kita tengok ya. Ya, dia boleh berubah ya if you change, if they move at different v, where the v is near the speed of light. Okay. So the most important thing here, you have to say it's something to do with time dilation. Yeah. Where we know that moving clocks run slower, meaning run slower means automatically we will age slower. But the thing is, how does the age get slower? So you need to say something about the relationship. Yeah, something to do with time do change with speed, where the speed, yeah, the faster the speed, the more time die later. So you can give this as an example, yeah. Okay, so this is how you answer this kind of question. Okay. Okay, so You say that what is the concept? It's something to do with time dilation. And then what is the implication of it? And then apa dia rumus dia? Kan dia kata with appropriate equation, yeah? So we use equation. And then what does it mean? Ni apa dia faktor penting yang membezakan, yang membolehkan they have to have different ages? It's something about the speed, yeah? And then we give a picture, yeah? Dia kata with appropriate illustration. So ada illustration, and then you give the example how to go about getting it. Macam tu lah, ya. That's how you go about, answering this kind of question. Okay, is there any question? Yeah, how to answer soalan-soalan sebegini? Ingat, ya. Whatever it is, go back to your basic concept. Daripada konsep tu, apa dia implikasi dia? What is the implication? And then, how does it change? Yeah? It's something to do with the speed. So, each and every one of them must undergo different speed. Then, only they can have different ages. Because, bila saya tengok your answers ni, most of you, stops here. Give this equation. And then, but you didn't say that, that you need to have different speed in order to have different ages. Okay, so the issue is time dilation, and it has something to do with different speed. Yeah, where the speed is near the speed of light. Where most of you did say something about near the speed of light, but you didn't say that different speed will give different ages. Okay. Now we go to the second question. Yeah, the second question says, second question says, an astronomer on Earth see a meteor hits the moon at exactly the same time as he sees a solar flare erupts on the sun. Yeah, according to the astronomer, the solar flare and the meteor impact are simultaneous event. So, is it true? We know that macam mana? Earth? Where are we? So, the astronomer is on Earth. Yeah. And then moon. Moon is nearer to Earth, isn't it? So, dia nampak meteor hits the moon. And then sun. Sun is very far away, isn't it? So, they see solar flare on the sun. Ya, dia kata, he sees it. Ya, dia nampak benda ni, both of this one at the same time. So, whatever that he sees is something that happens way before it, isn't it? Kita tahu simultaneous event are event. Macam mana kita nak define simultaneous event? Apa dia dua condition simultaneous event? Dia ada dua condition, isn't it? Dia mesti time of event same, tapi position different. So, if we see here that, of course, the position is different. Because kita tahu one is on the moon and the other is on the sun, isn't it? Dia kata time of event must be the same. Tapi, what can we see now? He sees the event at the same time. Tapi, And remember, time of event is when the event occurs, isn't it? Time of event is when event occur. Yeah, remember, it is not the time that you see it. Okay. But if you look at this statement, it says that, yeah, the astronomer on Earth sees. Nampak ni? Sees. Dia nampak. Hit exactly the same time. Yeah? Dia nampak benda tu berlaku at the same time. Nampak pada pandangan mata dia. But remember, time of event is when the event occur, kan? Not the time that you see it. Well, yang dia nampak same time is not, actually is not the time when event occurs. When events occur. Kan? Jadi kalau dia nampak this one at the same time, meaning kita tahu bahawa jarak sun and earth is very far away, ya. Kiranya the solar flare must have occurred first, isn't it? Ni solar flare must occur first. Dia tahu because jarak dia is distance Earth dengan Sun is much greater than distance Earth dengan Moon. Kan? So, kalau for it to see it at the same time, astronomer, the solar flare must occur first. Later baru meteor hit the Moon. So, sebab satu condition ni is not being fulfilled, kalau kita tengok case kita, solar flare must occur first, then statement ini adalah false, Okay, lagi sekali, An astronomer on Earth see a meteor, see dia nampak, wavefront daripada meteor ni, daripada meteor ni sampai ke mata dia. At the same time, wave yang cahaya yang bawa gambar solar flare ni reach dia punya eye at the same time. But the thing is, kita tahu bahawa simultaneous event dia ada dua syarat, time of event must be the same and then position different. Cuma satu saja syarat simultaneous event dipatuhi. Tapi syarat yang lagi satu, time of event must be the same, ni tidak berlaku, kan? Because remember, time of event is when event occur, and not time when you see it. Kalau kita tengok dari sini pun, since the distance between the Earth and the Sun is much greater than the distance between the Earth and the Moon, then, the wavefront yang bawa gambar ni untuk sampai ke mata kita should have occurred way before the moon, the meteor hit the Moon. So, kiranya ini adalah bukan, So, meteor hit the moon. Hit moon. And solar flare erupt on sun. Sun is not a Simultaneous event are not simultaneous events. Okay. Okay, nampak tak macam mana ya? Saya olahkan supaya it's easy for you to understand ya. The first thing that you should go about is kembali balik ke konsep asas dia. Ya, sebab dia kata this is something to do with simultaneous event. Okay, so kita pergi balik semula ke konsep simultaneous event. Kita tahu bahawa dia ada dua condition. Okay, condition pertama, okay, memang betul dia different places. So, alright. Tapi, syarat kedua pula. Ya, time of event must be the same. So, kita kena tengok pula ya, untuk case ini adakah dia punya time of event tu sama ataupun tidak. So, obviously ya, it boils down to ini dia. Ya, because kadang-kadang kita lupa ya. Time of event is when event occurs and not when you see it. Ini dia. Same time seeing it. Itu yang tak boleh tu. Ya, argument pertama dan argument kedua ya, something to do with the distance. Dia macam inilah, because this one comes from kita punya third video conference, isn't it? But the thing is, whatever that's being discussed in the video conference, you need to understand it. Because there are several students yang answer macam rupa assignment sidang video 3. Ada juga yang discuss macam apa yang kita bincang dalam sidang video 3. Yeah, but the thing is, kita kena tengok case ya, macam mana, how is it ya. Basically it's just penggunaan maksud simultaneous event. You need to understand things ya. You cannot just memorize, hafal and think that everything will be the same ya. You need to understand it. What does it mean? Every time you have to go back to the basic principle, konsep dia. Apa dia maksud sesuatu takrifan tu. Then you won't go far, ya. You takkan sesat. It's of no use for you to memorize things without understanding. Ya. Okay, is there any question? Jelas tak? Tengok dari tadi macam cara saya jawab pun kan. The first thing I will go back to the basic concept dia. Then apa implikasi dia? Ya. Sama juga yang ini kan. Saya pergi balik kepada konsep dia. Apa dia implikasi dia? Nampak tak? So daripada implikasi ni kita kembangkan lagi macam mana dia. Kan? Daripada implikasi ni, okey, apa dia lagi evidence dia? Jadi kalau if you follow this trend ya, strategi yang macam ini, insya-Allah takkanlah bermasalah. So, sebab saya rasa macam terpanggil ya, I need to discuss this with you. Okay. Next, jom kita pergi soalan nombor C. I guess most of you can answer this one lah ya. Because this is your assignment sidang video 2. Is it 2 ke 3 ke pertama? Saya pun tak ingat. So most of you can answer this one. Ya. Tapi ya, ada setengah tu dia cuma cakap secara umum saja. Dia kata okay, 10 meter pool. Dia kata okay, dia kata false Dia kata 10 meter pool can fit macam ni lah lebih kurang ya. 8 meter tanah. Dia kata something to do with land contraction. Okey, kiranya dia nampak lah ya. Ada juga setengah yang tulis ya. Dia kembali kepada rumus L is equals to L0 divide by gamma L0 square root of 1 minus V over C squared. Okay. Tapi the thing is, ya dia berhenti kat sini. Dia berhenti kat sini. Kalau berhenti kat sini ya, kiranya kan, give your comment on the truthfulness. Jadi kiranya kau sampai kat sini, macam you punya ni cakap cerita dia separuh jalan. Takkah? Sebab you dah tahu dah. You ada 10 meter pool. You dah tahu dah 8 meter tanah, isn't it? So you can boleh jawab dah benda-benda ni, isn't it? You akan boleh solve sampai habis kan? So kalau you masukkan, you akan dapat apa? L you berapa? L0 is equals to 10. L0. So ini adalah L. So kalau you masukkan dalam ini, so you akan dapat ya, L bagi L0 is equals to square root of 1 minus V over C squared. L over L0 squared 1 minus V over C squared. So you boleh dapat V over C squared 1 minus, so you boleh dapat V is equal to 0.6 C. Okey, kalau siapa yang jawab sampai ke sini, then you get the full marks. Siapa yang jawab sampai takat ni saja, separuh jalan lah ya. Next time kalau you nampak ya sesuatu yang diberi nilai-nilai sebegini, maka it's best that you solve sehingga habis. Okay, any soalan? Again, kalau tengok trend ya, saya akan every time saya akan balik kepada konsep dia. Lepas konsep, saya surely will go into the rumus apa yang berkaitan. Ya. And then disebabkan kita ada semua nilai, then saya terus to solve it. Tengok strategi dia. Begitu juga tadi, isn't it? Macam kes Adam tadi pun. Ya. Konsep. Pergi kepada rumus. Dan sebab kita boleh bubuh, sebab nak tunjukkan had laju yang berlainan, then kita tunjuk kiraan. Kita boleh kira. Begitu juga dengan kes ini tadi. Ya. Balik kepada konsep asas. And then apa makna dia. And then baru kita tengok dalam ini apa maksud yang ini. Then we solve. Okay. Okay, next kita pergi kepada soalan D. Okay, mass and energy are equivalent. Oh, okay. So, macam mana kita nak jawab soalan ini? Remember ya, Einstein punya equation apa? E is equals to mc squared. So okay, daripada sini kita boleh buat kiraan ya. Kalau ya ada kehilangan mas, ya, dia kehilangan mas ini akan berubah menjadi tenaga. Kalau anda lihat dekat mana kita punya textbook ya, textbook kita bukan surat berapa yang ada cerita benda macam tu. Okey. Ni kalau lihat kat bawah ni kan, dia kata mass and energy are not independent entities. Their separate conservation principle are properly a single one. The principle of conservation of mass energy. Mass and energy are different aspects of the same thing. Okay. Mass can be created or destroyed, but when this happens, an equivalent amount of energy simultaneously vanishes or come into being, or vice versa. Okay. So daripada ini ya, perenggan yang kat bawah ni mungkin ya, sebab dia dekat bawah sekali ya, tak ada siapa nampak ya. Okay, ataupun ya, E is equals to mc squared ya. Kalau anda masih ingat ya, ketika bom atom Hiroshima tu semuanya datang daripada ini ya, daripada jisim uranium itu kita dapat tenaga letupan tu E. So senang saja ya. Mass and energy are equivalent, yes, of course ya. Oops. Okay, so yes. Tu dekat buku kita muka surat 27, page 27 ya. So again ya, strategi saya kalau tengok, saya akan kembali kepada konsep asas. The basic concept mengenainya, and then I go straight to dia punya rumus ataupun equation dia ya. So next time if you would like to answer this kind of question, okay, go back to the basic concept and then look for the equation yang menerangkan relationship between one and the other, ataupun dia punya definition ya. So daripada definition itu kita tengok ya, macam mana kita nak kupas, macam mana kita nak comment. At least ya, your comment is ada guided ya. Okay, next. Okay, Adam is given the opportunity to do an experiment at the Stanford Particle Accelerator, USA. During one of his experiments, he detected the creation and decay of omega minus particle. From his calculation, the omega minus particle has a rest energy of 1672 mega electron volt and total energy 223 mega electron volt. He wonders whether the omega particle is a particle without mass. Help him by explaining your answer. So macam mana ni? Dia beri kepada kita the rest energy and also total energy. Total energy apa dia? E is equals to gamma E0 kan? Rest energy E0 is equals to C squared. Isn't it? Then nak cakap kat kita whether the gamma minus ni is a particle without mass. Obviously kita tahu bahawa dia ada rest energy, where rest energy is given by this one, kan? So we go back to the basic concept to relate mass dengan energy dia. So kita tahu bahawa E is equals to E0 is equals to mc squared. So ini is equals to 1672 mega electron volts. So kita tahu, so kita boleh dapat M is equals to E0 divided by C squared. Kan? Tapi takkan kita nak tinggalkan dia sampai takat ini saja. Whereas we are given all the values, isn't it? So 1672 mega. Macam mana nak convert mega? Mega bermakna 10 to the power of 6, isn't it? E, apa maksud E di sini? Apa maksud E? E adalah 1.6 times 10 to the power of negative 19. Ingat ya, kita nak tukar semua ni ke joules, isn't it? Energy must be in unit joules. Because C kita 3 times 10 to the power of 8 meter per second, isn't it? Kita nak tukar semua dalam unit SI. Kan? Mana dekat belakang ni saya rasa saya dah bagi dah ya. Ni charge of electron ni E 1.6 times 10 to the power of negative 19 ya. So, kalau buat kiraan ini, what you are going to get is 2.97 times 10 to the power of negative 27 ya, kilogram. Ya, kebanyakan pelajar ya, dia tak buat ini, dia tak buat bahagian ini. Tukarkan mega ni dan tukarkan E ni. Ramai tak buat yang ni, benda dua. Ada setengah buat yang ni, tapi yang ini tak buat. So next time kalau tengok ya, mega electron volt ni, mega 10 to the power of 6, E ni kita kena tukar ya, 1.6 times 10 to the power of negative 19. Then baru dapat M yang betul. Okay, ada apa-apa soalan kat sini? Oh, semua orang nak tengok saja. Tak nak komen pun, tak nak tanya. Tak mau tanya pun, nak tengok saja. Tak ada soalan? Okay. Then okay, dia kata pula, if the gamma minus, if the particle decays and leaves a track 24 mm long, what is the speed of the particle when making the imprint on the track? Speed dia. So, dia nak speed. So, macam mana kita nak buat tu? Dia nak speed. Dia cuma bagi kita length. Ada juga setengah student ya, dia nampak saja ya, track ni panjang, diberi panjang, itu dia kata V is equals to apa? L divided by T. Dia terus je gitu. Kita ada L, tapi kita tak ada T. Macam ni kita nak solve, isn't it? Tapi apa yang kita ada, so definitely kita tak boleh guna pada takat ini rumus ini, isn't it? Tapi dia ada beri pada kita apa? Dia ada beri pada kita total energy. So E is equals to gamma E0 kan. Kita tahu E0, kita tahu E, then gamma pun kita tahu, isn't it? 1 over kan ada ungkapan V kat dalam tu, isn't it? So dengan guna rumus ini, maka kita boleh dapat kita punya V. Okey, nanti balik rumah ya, daripada rumus ini, guna yang ini ya, pastikan ya dapat V is equal to, jawapan dia 0.696C. Ingat ya. E dengan E0 ni dia apa? Mega electron volt ya. Ingat. Ini mega electron volt. Tapi kebetulan ya, sebab kita akan dapat apa? E bagi E0 is equals to 1 per Okay, so kita akan balikkan dia. So kita akan dapat 1 over sebab kita dapat ini, then mega electron volt dia cancel. Kebetulan saja ya. Kebanyakan student boleh dapat soalan ni betul sebab ya mega electron volt kat atas cancel dengan mega electron volt kat bawah. Okey, cuba buat sendiri ya, pastikan dapat jawapan ini. Okey, next. Momentum of the particle. So macam mana pula ya momentum of the particle? Ingat ya, ada setengah yang masih menggunakan Okey, ni salah ya. Nampak kita punya V adalah 0.696C. Dah nak dekat dengan mana boleh guna persamaan ini? Kita perlu guna, isn't it? Gamma kita boleh cari dah. M kita boleh cari sebab soalan A kita dah jawab. V kita dah cari dalam soalan B bahagian 1. So P jawapan dia ya, cuba buat sendiri. Jawapan dia adalah 8.64 times 10 to the power negative 19 kilogram meter per second. Okey, cuba buat sendiri ya. M dah tahu. M dari tadi. Soalan ni tadi. Ya. Ni nilai dia. V kita tahu. Then bolehlah dapat. Okey. Distance travel according to the particle. Macam mana pula ni? Dia beri pada kita. So kalau anda lukis balik, macam mana? Dekat. So ini partikel. Ini dekat left. Jadi ini adalah zero, isn't it? So partikel And soalan last sekali. Kata apa? Oh, mean lifetime. So L0 lab particle. So kat sini L. So T. So T kat sini adalah T0, isn't it? Because ini dua places, maka this one is T. Kita tahu V L divided by T0. So kita punya T0 adalah L divided by V. L kita tadi 17. V kita 0.696. 3 times 10 to the power of 8. So soalan kita apa? Oh, okay. So macam tu lah. Ingat tak masa yang you all buat worksheet 5, isn't it? Kita must datang daripada rangka rujukan yang sama. Ingat, mean lifetime adalah pada partikel. So T0 adalah mean lifetime, isn't it? Itulah dia sedikit. Not bad. Okay, tak apa. Nanti balik rumah pelan-pelan tengok. Tengok balik konsep dia macam mana, how to go about doing it. Okay. Kat mana yang tersalah tu. Remember, whatever it is, you must understand it rather than menghafal. Kalau menghafal memang tak guna. Okay, ada apa-apa soalan setakat ni? Okay, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. So, this is our 5th video conference for JIF 103 Physics 1. So, I wonder who's in Kuala Lumpur, please. Just sit next to the ni. Oh. Yeah, bring all your stuff near there. So, it's easier. Okay, so.
Good afternoon, Prof.
Yes.
I'm Selvam here.
Okay.
I'm the only one here in KL.
Okay. Okay, Savam in KL. Who's in Nibung Tebal?
Huzaifah and Tamizi.
Huzaifah and Tarmizi. Okay, Tarmizi. Okay, so who's there in Kota Baru?
Hafizu.
Okay, Hafiz. Okay. Saya dah terlupa dah macam mana nak pergikan ke PC. Wait, let me see. Hide selfie. You boleh nampak apa yang ni ke?
Tak ada apa-apa, bro.
Oh, tak ada apa-apa. Can you see me?
I can see you, but on the other screen, I can see myself, the whole TV.
Wait. I forgot how to change the... I
okay,
forgot.
okay, now okay.
Okay. I forgot how to do it because it has been a long time. Okay, so what we're going to talk about today is the characteristic of light, specifically what is light. So to you, what does light means? Come on.
Wave and particle.
Oh, wave and particle. Amboi, Hafiz dah tukar pemikiran dah. Okay. Alright. What about you, Salvam? Is it wave and particle or still wave? Yes, Salvam tak dengar. On the microphone.
Okay, what I've read is first light was considered as a wave. But then later they found out it can be a particle.
Okay. Alright. Now, I mean, you as a person, what do you think light is?
I think light is a particle.
You think light is a particle. Okay, what about you, Huzaifa and Tarmizi? No, just offhand, what do you think? Come on, Huzaifa. You don't have to flip your book. What do you think?
Okay, I try to answer your question. What is light?
Yes.
Light is move 3 times 10 to the power of 8.
Oh, it's something that moves at 3 times 10 to the power of 8. Alright. What about you, Tarmizi? Oh, flip.
I have no idea.
You have no idea. Oh, great. A blank slate. Okay, basically, as what Salvam said, people used to think of light as a wave, isn't it? Classical physics still up to now say that light is a wave, where normally when we refer to light, it's visible light, but actually light can have it can go to ultraviolet, it can go to infrared. So it's not only visible but from ultraviolet to infrared. Okay, but from your lab work, you did learn that light indeed is a wave. So what are the evidence that you have learned in your lab? What is the evidence that you have learned in your lab that says that light is indeed a wave? If you can recall during intensive course, I see that most of you have very, very high marks. So I wonder whether it really seep through into your mind or what. Most of you get around 80 to 90. Whew. Okay, so what does it mean to you? What does it mean to you? What are the evidences that you have seen that says that light is indeed a wave? Masa kursus intensif, what do you do? Tak ingat dah. Yang double slit, isn't it? You did that one until? Kan?
Yes.
Yeah, you saw the interference fringes, isn't it?
Yes.
So the interference fringes is an evidence that light indeed behave as a wave. Okay? There's another one, diffraction, isn't it? When you use a single slit. Remember, you change the plate. First, your plate is double slit. And then you change the plate, you put single slit. And indeed, you see also brightness and also darkness, but with various intensities. That one is called diffraction. So whenever you see something that shows diffraction fringes or interference fringes, that means the source is a wave. Okay? Agree?
Yes.
So evidence that shows that anything is a wave, they must either show interference fringes or diffraction fringes. So if you see that, means the source is a wave. Okay? But now, actually there's the other side of light, isn't it? But let's say we have a positive or negatively charged zinc plate. And then we have a red laser light. When we shine our laser light to the plate, nothing happens. If we change the red laser light to ultraviolet light and we use a positively charged zinc plate, again nothing happens. When we have a negatively charged zinc plate and we use UV light, what happened was this flap here falls, this leaf falls immediately. Immediately, the word is immediate, yeah? Why? Or shall we have it as sidang video 5 punya assignment? Well, never mind. Let's go through the topic of our discussion for our sidang video. But keep this one in mind. How are you going to explain this? So basically, before going to whatever that we are going to do, you need to know these 3 characteristics of light energy from either classical theory of energy and also quantum theory. Classical theory of energy says that light behave like a wave. But the quantum theory says that light have also particle nature. So, from these two views, two models, what are their characteristics of light energy? So, in classical theory, it says that energy of light is continuous. Jot it down somewhere. Make a table. Jot down somewhere because we are going to use these properties. Yeah, classical theory says energy of light is continuous. Okay. And then it says that the intensity, the energy depends on the intensity. Or I is proportional to energy is proportional to the intensity. So, the more intense the light is, ataupun the brighter the light is, maka the higher the energy will be, and meaning more available energy. Okay. Jadi, the brighter the light is, meaning the light propagates at a higher energy. So, if higher energy means more available energy. So, that's what classical theory of energy says. And energy of light takes time to be accumulated. Why is it so, isn't it? It takes time. Why? Because, let's say we have a candle, a candle, and then we know that the light energy will propagate, since it's a point source, you will see that the wavefront of the light will move radially. But actually, it moves radially. The energy, is evenly distributed across the wavefront. Jadi, kiranya the energy is distributed across this wavefront. Alright? So, let's say we have point B here. Jadi, as time increases, then more light energy can be accumulated. So, it takes time, to accumulate the energy because the energy is distributed evenly across the wavefront. So, that's why it takes time to accumulate. Jadi, senang je nak ingat, Kalau nak ingat, biasanya saya just use Okey, saya ingat C, ya, C I T, sit. Ya, macam tu je kita nak ingat. Ya, light property kalau classical theory CIT. Continuous, depends on intensity and it takes time. Okay, kita guna akronim lah, mnemonics. Nak bagi ingat ya, continuous, depends on intensity and it takes time. Is there any question about the property of light property ni? Okay, tak ada Just remember that it is CIT. Continuous, depends on intensity and takes time to accumulate. Now kita tengok pula for the case of quantum theory. So, quantum theory says light energy is quantized. Yeah, and the energy depends on the frequency. Kita punya textbook kata apa ya? Kita guna simbol apa dalam textbook? E. Kenapa saya punya ni tak pen. So E. Kenapa saya punya ni hilang? Let's say in color. Oh, sana. E is proportional to frequency. Kan? Okay. Alright. E is proportional to frequency. Alright. But, and also the light energy can be absorbed or emitted spontaneously. So itulah dia beza dia. Ya, yang ini discrete ataupun quantized, depends on frequency. Yang ini depends on intensity. And then this one can absorb or emitted spontaneously. Itu dia beza dia. So, kita akan gunakan ya, nak tengok which of the characteristic of light energy yang can explain ya photoelectric effect shortly. Okay, kalau ini macam mana nak ingat ya? Kita guna D. Kita guna D, F. DF macam mana? Spontaneous. DFS. Okay, discrete, depends on frequency and spontaneous. DFS. CIT, DFS. So it's about whether it's discrete or continuous, whether it depends on frequency or it depends on intensity, whether it's spontaneously absorbed or takes time. Okay. Is there any question? If not, we continue. Ingat ya, CIT, DFS. Okay, now now we are moving from the classical that says like that light behave as a wave. We are moving into the world that light behave like particle, which is essentially what Einstein get his Nobel Prize. Example ya, kalau kita guna untuk remote control for our TV, so we are using the property of light as a particle. Why did I say that we are using the property of light as a particle? Kenapa bukan light as a wave?
Because it's spontaneous.
Yes, because it spontaneous. Kalau dia a wave, then it takes some time untuk accumulate untuk TV kita response. Okay. Actually, there are 3 evidences of particle behavior of light. So, apa dia 3 tu? That if you have read in your textbook. So, your textbook did give 3 example. What are the examples? Okay, Sarmizi dia nak flip the pages of the textbook. Okay. Go ahead. Okay, apa dia? Okay, Hafiz, apa dia? Mesti Hafiz dah baca dah ni. Textbook kata? Tak baca lagi, Hafiz? Takkanlah tak baca. Apa dia? On the microphone.
Lupa.
Oh, lupa? Kawan kita dekat Pulau Pinang tu siapa? Seorang tu. What is it? Okay, Selvam pun baru nak terselak-selak. Okay, apa tu Selvam? What is it? 3.
Pun dah lupa tengah cari.
Okay. Chapter 2 kan?
Photon.
Okay, photon tu kiranya packet of energy tu, kalau kita particle nature, kita panggil light tu sebagai photon. Itu nama glamour bagi light lah. Ya, photon. Photon is actually a bundle of light energy. Okay. Kan dalam photoelectric effect, isn't it? Yang ini sebenarnya you are going to learn it, you are going to buat amali next year, tahun 2. Ya, satu evidence dia photoelectric effect, there is when light falls on metal surface, ya, akali punya metal surface, then you can detect electron being ejected out from the surface. Depends on the light with sufficient energy. Then you get this electron being injected from the surface. So this is called photoelectric effect. Ya, lagi satu X-ray production. Ya, X-ray production is actually another evidence that shows that light behave like a particle. You can read more inside your textbook. And another one is Compton effect. Where incident X-ray kena pada elektron, tiba-tiba elektron tu pula can be recalled macam rupa saja collision. Kan, kalau bola biliar, satu melanggar the other one, satu akan pergi ke this oblique angle and another one to the other angle opposite. So kita tengok this, even though it's a wave, kalaulah kita kata dia a wave, how can wave boleh berlagak macam bola biliar, isn't it? So ini menunjukkan Compton effect juga merupakan satu evidence, one evidence of the particle behavior of light. Jadi kalau kata 3 evidence, it's photoelectric effect, X-ray production, and also Compton effect. Kan, in X-ray production, elektron bila dia lalu near the nucleus, because of it of the attraction force, being attracted, so dia berubah arah, and normally its speed decreases. When its speed decreases, part of its energy is released in a form of X-ray.
Kalau dalam kamera tu macam mana tak?
Dalam kamera? Kamera macam mana? Yang which one? Kamera? Maksud dalam kamera tu macam mana?
Kan kamera digital dia cahaya pun ada.
Yes, something like that. So, biasanya bila light falls on the solid state device yang dalam kamera tu, kemudian elektron ni akan keluar daripada that then you get your signals. Then you get your data lah. So, dia jadi digitize benda tu. Whatever lah yang menunjukkan gambar tu. So, it's this principle. Ni, photoelectric effect. Okay, now hari ni kita are going to talk about photoelectric effect saja. How are we going to explain this phenomena? Why light, when it falls on this metal, and then electron can be ejected? Why is it like that? So we have started with the wave behavior of light, but now we are moving pula towards we did talk something about light do behave like a particle. Dia ada 3 bukti, tapi now we are going to isolate cuma 1 bukti saja, photoelectric effect. Describe photoelectric effect experiment setup, and then state 6 photoelectric experimental observation, and then we try to explain it. Why is it like that? We try first nak guna classical approach, because that's the way how people did it before. Tapi there are some of it that we cannot explain using classical approach. Then we have to go using Einstein punya particle postulates. Tak apa, kita go pelan-pelan, and then if you don't understand, kita berhenti kat situ. Okay. So, biasanya dia ada vacuum tube, and then dia akan ada emitter, and then collector kat sini. And then of course we are going to have our voltmeter dengan ammeter, ataupun schematically kita ada vacuum tube supaya tidak ada resistance ataupun apa-apa yang akan menghalang pergerakan elektron kita. So we have the emitter, yang mana kita boleh ubah jenis metal bagi emitter ni. And then we have our collector, and then of course we have our light source, the source of energy. And then, when light of sufficient energy falls on our emitter, electron is ejected. At times, this electron is being called photoelectron. Because dia dihasilkan oleh cahaya. So, it's called, another name for it is photoelectron. Be careful, photoelectron tak sama dengan photon. Apa dia perbezaan di antara foton dengan fotoelektron? Apa term tu? Istilah. Fotoelektron dengan foton. Apa perbezaan di antara kedua tu?
Bundle of energy.
Okay, kalau foton, bundle of energy. Kalau fotoelektron,
it's the electron, the negative charge of from the light.
Okay. So photoelectron is the electron that has been ejected from the emitter, hasil from the light source. So it's called, sometimes it's called electron saja, sometimes it's called photoelectron. So light ini, nama glamour dia is photon. Bundle of energy. Kalau kita cakap daripada perspektif light as a particle. Okay. So, selain daripada itu, we have this variable DC voltage. So, selain daripada itu, we have this variable DC voltage, yang mana we can use this DC voltage punya source ni to get to know what is the maximum kinetic energy of the electron. Nanti sikit lagi saya akan tunjuk. Then of course we need to have our ammeter. Nak tengok the current that's being produced. Tengok the terminal for the voltage source. Kalau positif, sini positif, then this one positive. But we can change the terminal of the voltage source supaya sini jadi negatif, sini jadi positif. Okay, kita boleh jadikan sini negatif dan sini positif. Jadi kalau sini negatif, then what happen? Agaknya apa akan berlaku ya? Kalau sini negatif.
Elektron akan ditolak.
Okey, elektron akan ditolak kecuali elektron yang kuat, sangat-sangat kuat saja yang boleh mengatasi the repulsive force, isn't it?
Yes,
But it's up to a certain point, isn't it? Because tenaga elektron ini juga bergantung kepada the incident light, isn't it? Okay, tak apa. Sikit lagi kita tengok. Yeah. Okay, now. Ini ada simulation. Let's see ya. Apa yang akan berlaku? Okay. Let's say kita letak our light is at the maximum dekat UV. Voltage kita letak kosong dululah. Ke nak letak positif? Tak positif lah. Ya. So, katakanlah we bagi intense light. So, see, nampak tak? Okay. So, the minute aja intensity, dia fotoelektron tu keluar secara ada masa, ada time lag ke tidak? Ada time lag ke tidak masa dia nak keluar? Jadi the minute aja light falls upon it, then spontaneous. Jadi kalau kita nak guna classical energy punya karakteristik, can we explain that?
No, cannot.
Cannot. So we have to use kita kena guna apa?
Quantum theory.
Ya, kita kena guna quantum theory. Now, look at the mari kita tengok ya graph current dengan ini. As we increase the intensity, apa berlaku? Apa berlaku? Ya, more particles. More particle means apa in terms of current?
More function.
More particle means more current lah kan, isn't it? Because current is bilangan charge bahagi massa. So the more charge yang kita dapat, maka the current will increase. But the thing is, current will increase. Jadi macam mana? Can we explain it using classical? Classical boleh explain tak ni? More intensity, more bilangan elektron yang keluar. Can classical explain that? Apa classical kata mengenai intensity? The more intense light is, the brighter the light is. What about the energy?
Increase.
Okay, the energy increases. So, energy increases means more electron can come out. Kata di classical lah ya. Tapi one thing, kalau kita tengok daripada aspek electron energy dia, kalau saya increase intensity, even though the number tu bertambah, even though the number bertambah, bila increase intensity, walaupun the number bertambah, tapi energy of each electron is still the same. Kan? Selvam, are you out from the video conference? So, walaupun bilangan banyak, increase the number, but the energy of the electron is still the same. Can we explain this phenomena menggunakan classical? Cannot kan? Jadi kita kena guna Quantum kata apa?
Energy increase with frequency.
Sebab bagi kes ini adakah saya tukar frekuensi? Saya cuma tukar intensity saja, isn't it? I keep my frequency constant. Saya tak ubah ya. Okay. So do you understand tak? Jadi if we increase our intensity, bilangan will increase but having the same energy. Cuma the increasing of intensity saja boleh diterangkan oleh classical. Kau classical kata increase in intensity, more available energy. Tapi ciri elektron yang tenaganya tidak berubah, tidak boleh, cannot be explained by the classical energy. Because energy, classical kata the higher the intensity, the more available energy. Tapi apa pasal pula elektron tu tak dapat more energy? Cuma bilangan saja bertambah. So dia tak boleh nak terangkan yang itu. So we have to go to the classical, sebagaimana kata di Hafiz, that the energy of the ejected electron depends on frequency. Let's say saya tukar frekuensi saya ya. Kalau saya tukar frekuensi saya tambahkan saya punya frekuensi. So what do you see? Bila kita tambah frekuensi, kita punya tenaga of each photoelectron increases. Ada bilangan dia bertambah? Ada bilangan dia bertambah? Ada ke bilangan dia bertambah kalau saya tambahkan frekuensi dia?
Bilangan tak tambah.
Bilangan tak tambah. Tapi kalau kita nak tambahkan bilangan, what do we do? Kalau nak tambah bilangan, kita kena buat apa?
Intensity.
Okay, kita tambah intensity. Kalau kita nak tambahkan energy of each photoelectron, maka kalau kita nak tambahkan energy of the electron tu, ejected electron, kita mesti tambah
Kena tambah intensity lah.
Intensity. Kan intensity tambah, cuma dia tambah bilangan saja kan. Tapi kalau nak tambah energy dia, kita kena tambah apa? Frekuensi. Sebab energy of the electron depends on frequency of incident light kan. Tengok kalau saya turunkan frequency of incident light, tengok dia turun kan, energy tu turun. So energy depends on frequency, kata di quantum theory of light. Okay. Tapi kalau saya katalah intensity saya bawah, so saya naikkan intensity. Tak boleh. So tapi kita tengok ya, kalau kita turunkan frekuensi tadi, saya kan kat sini kan, tapi bila saya turunkan, turun, tengok sampai ada satu takat tidak ada lagi fotoelektron yang keluar. Tu ada. Tapi bila saya dah sampai dekat kuning ni, dah tak ada dah fotoelektron. Current pun dah kosong dah. Okey, dah tak ada. Kenapa tak ada fotoelektron pula? Dia macam ada cut off, dia macam ada threshold frekuensi. Kat sini ada dah. Ada balik. Tapi kalau kita pergi ke rendah, kita kurangkan frekuensi, tak ada. Tak ada fotoelektron keluar. Kenapa tak ada fotoelektron keluar? Walaupun intensiti kita dah sampai 83. Katalah kita naik intensiti kita sampai 100%. Tadi kata kalau kita bagi light yang intense, bilangan akan bertambah. Tapi now dah sampai 100% intensity, tak ada langsung fotoelektron yang keluar. Mengapa begitu agaknya ya? Why is it like that?
Kinetic energy of electron depends on frequency.
Ialah kinetic energy dia depends on frequency of incident light. Okay. Tapi ialah itu kinetic energy dia. Tapi untuk pengeluaran, to get it to be ejected, apa? Dia mestilah apa? The incident light must Kayaknya the incident light tu must have sufficient energy kan untuk keluarkan elektron tu daripada that metal. Kenapa macam tu? Why is it like that? Kenapa kita ada a minimum amount of energy? Kenapa?
Because electron needs a minimum energy to release from the surface.
Yes. Energy tu dipanggil work function. Jadi kiranya when the incident light ni, the incident light must have sufficient energy to keluarkan elektron kita daripada metal surface. Kita tahu bahawa the electron is bonded to the nucleus kan? So kita mesti break the bond, then only our electron can come out. So inilah dianya. Jadi frekuensi yang mana ya, yang pada takat yang dia baru nak keluar tu, ya, yang ni tak kena. Wait, kat sini. Dekat yang sejurus sebelum nak keluar ni, ini dipanggil threshold frequency. Tengok ni. Kan ni kat sini, ini dipanggil threshold frequency. So, light must, ya, minimumnya bernilai threshold frequency. Selebihnya akan, kalau kita tengok kat sini, ya, kalau kita naik sikit aja, baru ada elektron keluar. Okay, where is it? Jadi kiranya, light yang jatuh ke atas metal ini, mestilah, okay, saya tulis. Kat sini tak boleh tulis. Okay. So light yang jatuh ni, kalau dia sama-sama saja dengan frekuensi threshold frekuensi, maka elektron boleh keluar tapi tak ada energi nak gerak. Kiranya bahagian lebihan daripada tenaga insiden ni, kalau dah melebihi daripada energy work function itu, baru elektron ada energi untuk gerak, ya, to move across this one. However, ya, katakanlah ya, so kiranya dia ada threshold frequency untuk pengeluaran elektron. Our incident light must have sufficient energy untuk keluarkan elektron. Now, katakanlah ya, kita pergi to the higher frequency. Tengok kan? Tengok graf ni. Boleh nampak kan? Energi fotoelektron tu makin bertambah. Kan? Energi dia makin bertambah. Kalau kita so inilah yang dipanggil ya fotoelektron punya graf. Is actually H nu daripada light tolak H darab dengan threshold frequency, kita dapat this energy. Kita boleh tahu ya berapakah energi elektron ini kalau kita set dia. Tengok ya, saya kurangkan dia punya voltage ni, jadikan dia negatif ya. Jadi ini instead of positive, kolektor ni saya akan jadikan dia negatif. Saya jadikan dia negatif. Ya, tengok-tengok dah jadi negatif. Jadi ada lagi elektron boleh sampai ke negative plate tu, dia boleh melawan the repulsive force, tapi sehingga kepada satu takat yang mana saya tengok dia dah start patah balik dah. Ya? Current dah tak ada dah. Kan, current dah habis kosong. Sebab dia tak boleh capai. So pada ketika ini apabila ya, so this is the ini dipanggil stopping voltage. Ataupun kita boleh dapat gunakan nilai ini untuk tahu apakah dia maximum kinetic energy of the electron yang ejected ni. Sebab walaupun elektron ni boleh gerak dah maksimum, tapi dia tak boleh nak lawan lagi the repulsive force. So this is called the stopping potential, yang mana kinetic energy K is equals to EV kan. Jadi V tu adalah V stopping potential ni. Kalau saya tinggikan balik, dia boleh sampai balik current. Tapi kalau saya turun sampai satu takat, current dah kosong. Dia tak sampai. So ini stopping voltage. Nanti saya akan letakkan dalam portal so that you can play around, get some idea ya, apakah dia interaksi dia di antara laju cahaya, frequency of light, the stopping voltage, the energy of the photoelectron, and then bilangan photoelectron. You tengok ya macam mana, apa yang menyebabkan photoelectron bertambah. Ya, apa yang menyebabkan tenaga elektron bertambah? Macam mana kita nak tahu nilai tenaga kinetik maksimum bagi elektron itu? So dia ada ya. Biasanya kita tengok, nak tahu kinetic energy maksimum, kita tengok the stopping potential, yang mana elektron tak boleh sampai ke collector. Current kita pun kalau tengok kat sini kosong. Okay, yang mana yes, kita dah lalui tadi, kebanyakan daripada fenomena ini tidak boleh diterangkan dengan menggunakan ciri gelombang bagi cahaya, isn't it? We cannot explain it using the wave property of light. Kita cuma boleh terangkan dia sepenuhnya dengan menggunakan ya ciri particle wave nature of light. So ada apa-apa soalan setakat ini? Nanti saya akan uploadkan so that you can play around. Tapi tengoklah ya, dia punya karakteristik itu macam mana. Adakah you boleh explain dia dengan menggunakan model light as a wave, ataupun you perlu gunakan model light as a particle. Ciri-ciri 3 tadi yang kita sebut tadi, CIT, DFS tu kan, anda dah lihat tadi, observation, current versus intensity, instantaneous current ya, current when light frequency, current for any view, and ni classical tak boleh explain, and okay, V stop different from weak and intensity light, sebab light bergantung kepada energy of light bergantung kepada frekuensi, dia tak bergantung kepada intensity. So sebagaimana yang saya dah sebut pada awal tadi ya, sebenarnya ia berdasarkan kepada light discrete quanta ya. Kiranya E is equals to H nu equals to H, product of H and frequency, or frequency kita tahu adalah C over lambda. Okay. Oh, saya dah tulis dah kat situ. Okay. Okay, alright. Jadi, and postulate kedua, light kuanta, kiranya dia absorb light ni satu-satu kuanta. Dia tak ada potong-potong ya. Dia tak ada macam rupa wave. And of course, one light quantum diberi kepada one electron. Tadi kita dah tengok ya, kita dah nampak dah this graph. Yang mana graph ni kita boleh tuliskan rumus dia. Ya, H nu ya, energy of the incident light is equals to energy of is equals to work function campur dengan kinetic energy. So this is the kinetic energy. K max, yang mana kita dah tahu dah ya macam mana nak dapat V stop tu. Ketika V stop, no electron reaches the collector. Pada ketika itulah kita boleh tahu tenaga kinetik maksimum bagi elektron kita. HF ya, sub-zero adalah work function. So this is the amount of energy yang perlu digunakan bagi mengeluarkan elektron daripada permukaan metal. Ini dipanggil threshold frequency. Threshold frequency. Ada lagi satu lambda zero. Lambda zero adalah wavelength, threshold wavelength. Ini adalah energy of the incident light. Yang mana kita tengok the energy tu senang saja. So ini menunjukkan bahawa energy tu satu bundle bundle ataupun satu package ataupun suatu kuanta yang diberikan oleh rumus H nu. So ni incident light. Jadi energy of the incident light, diberikan untuk mengeluarkan untuk mengatasi work function, melepaskan elektron daripada ikatan atom dia, dan selebihnya digunakan untuk pergerakan dia. Yang mana Kmax diberi oleh rumus E darab V stop. So inilah dia rumus yang memberikan Einstein Nobel Prize. So kiranya one light, one electron ni, kiranya dia macam bagi je, macam seketul saja bagi energi tu. Tu sebab dia boleh spontaneous. Tapi kalau berbentuk gelombang, dia kena accumulate lama, dah cukup energi, baru boleh. Ini lain sebab dia satu bundle of energy, dia bagi je macam itu. Macam kita bagi bola lah tu sebabnya dia spontaneous. And absorption pun dia mesti absorb light satu kuanta sekali. Kiranya setiap kali dia akan absorb H nu. Dia tak ada absorb half H nu ke, 1/3 H nu ke, tak ada. Dia mesti macam ni. Kalau light tu punya energi macam ini, dia terus saja absorb sekali saja, tak ada pecah-pecah. Dia absorb pun dia mesti absorb banyak itu saja apa yang ada. So itulah dia macam mana light, ciri-ciri light behave as a particle yang kita boleh dapati daripada photoelectric effect. Okay, kita nak go to kita punya ini balik semula ke, ataupun you would like to do it as assignment?
Boleh buat assignment.
Okay, boleh buat assignment. Dah dapat idea dah lah kenapa benda tu begitu? Okay. Then is there any question? Because we have only 1 more minute because the next class coming in. Okay, thank you everyone. So sebentar lagi insyaAllah kita jumpa 104 in 1 hour's time. 6 video conference. I've divided it into 2 parts. One is the conceptual part and the other part is the calculation. So as I've written in the academic planner, so this time we are going to talk about, does matter have wave-like properties? But it seems that from your assignments, I can see that most of you can answer the conceptual part. But anyway, there are things that you need to know, perhaps something new to you. So basically what we are going to talk about is, of course, we recall the wave-particle duality of light as a basis for our discussion. And later I will talk about evidences of wave behavior of matter, by using electron double slit experiment instead of light double slit experiment. We can also use particles instead of light. And next is about diversion gamma electron diffraction experiment, and also by using atom interferometer. So these are the three evidences that shows that indeed, particle, whether it's electron or neutron or proton, will exhibit wave behavior. But the thing is, as for us, we do have this wave, but the wavelength is very, very small. That's why we couldn't see it. But for this nano material, because it's small enough, and our detection devices is able to make us see the effect of the interference and also the diffraction images. Okay, as we know that light have dual properties, wave particle duality. So wave, the evidence of wave is the evidence of wave for light, wave nature of light. Where can we see it from? I mean, we have talked about it last class, last video conference. So what are the evidence? Where can we see the evidence? As for particle, we know is by using photoelectric effect. But for light, for the wave, nobody answering.
The double slit.
Okay, double slit, and also
The single slit.
okay, single slit, diffraction images. Okay, so we can see the interference, double slit, and also single slit ataupun diffraction grating, isn't it? So we can see the diffraction part of it. And for the particle nature of light, we can see it from the photoelectric effect. Apart from photoelectric effect, apa lagi yang boleh membuktikan that light indeed have particle properties? Apa dia lagi selain daripada photoelectric effect? Apart from photoelectric effect, what else that shows particle properties of light? Ain, you should be able to answer because otak dah cair dalam panas. Lihat. Apa dia? Hafiz? Apa Hafiz? Selain daripada photoelectric effect, what else can show particle nature?
X-ray.
Apanya?
X-ray.
Okay, the formation of X-ray, isn't it? The Bremsstrahlung, kan? Is actually the inverse of photoelectric effect, and in fact it did shows the particle nature of light. Okay, selain daripada itu, there's another one. Selain the photoelectric effect and formation of the breaking radiation, formation of X-ray, and another one is ada tiga sebenarnya yang exhibit particle nature of light. Ada lagi satu. Apa dia?
Yang compact effect tu atas.
Yang compact Compton effect. Yes. So tiga lah yang menunjukkan particle behavior of light. Photoelectric effect yang the most famous one. Next is the Compton effect. Yang lagi satu is the inverse of photoelectric effect, iaitu the breaking radiation of light. X-ray, the formation of X-ray. So itu tiga lah So itu pasal wave particle duality of light. But now Louis Broglie ni, setengah orang sebut dia Broglie, ada setengah orang sebut dia Brock saja. So it's up to you lah because the American normally say Broglie, but the French say Brock saja. So it's up to you lah. Okay, sebab look at the way he thinks. Okay, he said light normally thought as a wave can act like a particle. And then he said there is a possibility that nature being symmetric. So then object normally thought as a particle would act like a wave. So nampak tak the way dia punya thinking? This is his PhD tau. His PhD work, and he get Nobel Prize for it. So such a simple thinking, but he at that particular time he couldn't really show the evidence for his thinking, because pada waktu itu tak ada lagi dia punya experimental evidence. It's just the theoretical part of things. And he said matter or particle have wave-like properties. From there, from thinking dia that nature being symmetric. But actually nature is symmetric. Kalau you tengok kan, there's a lot of things, Is kalau you tengok, there's the pairs of it. So we call it matter waves, because to make things easy. So, kalau kita kata matter waves, then there must be evidences, because like light just now, we said that if wave, anything that have wave properties, it can show interference and it can show diffraction. Jadi, what about untuk matter wave, Can we see the interference fringes? Can we see the diffraction fringes? But the thing is, if you look around us, being big object, we didn't see any fringes, isn't it? How can Broadly, dares to say that nature is symmetric, whereas around us we didn't see any fringes? But perhaps, scientists thinking that nature basic building blocks being electron, proton, and neutron, or perhaps we can see it at the nano level. So, then it comes here. Then, instead of light being used in this young double slit experiment, if we replace the light source with electron, are we going to get the interference fringes? Kalau wave, dia punya properties, we can see it in the interference and diffraction. If benda ni if matter wave does exist, then kita mesti boleh lihat the interference fringes from the electrons. Even though to us, electrons are particles. So, instead of light, now we use electron in the double slit. So, we get something speckles here and there. If we use about 100 electrons, we still see the particle nature. Because it spots here and there, we didn't see any interference pattern as yet. If we see about 3,000 electrons, then we are beginning to see, that's this one, the dark part, and this one there's more electrons here compared to this one. So we are beginning to see interference fringes. But when there are more electrons, about 70,000, we can see clearly the interference fringes. So, this shows that, indeed, electron do exhibit wave nature. So, kita boleh kata lah, yes, that matter wave do exist. Okay. So, this is the evidence that matter have wave-like properties, electron double slit experiment. Okay, so that's the interference, But now, what about diffraction? Does electron also shows diffraction fringes? Okay. So, if light, diffraction fringes here is something like this, If we let it go through crystals, we can also do such kind of experiment, Instead of light, kita guna electron. Where we irradiate crystal lattice and we get our diffraction effect. So this is actually the experiment being done by Davison and Gamma. Not sure which one is Davison and which one is Gamma, but both of them are doing experiment, if I'm not mistaken, under Rutherford. So whenever the electron hits the crystal, so we can get the diffraction fringes, just like the one that we have for light. So for electron, kita pun boleh dapat, sebagaimana macam light juga. And for neutron, we do get it like that. So, kalau macam ini, kita boleh kata apa? Matter indeed have wave-like properties. So, it can shows both diffraction and also interference fringes. Nanti sikit lagi kita akan tunjukkan mathematically how we can get to show that electron indeed have wave-like properties. So I know from your tugasan, most of you can answer this one. Surprisingly, a lot of you did get A, isn't it, for your coursework? But that one is thanks to your video conference assignments, I don't think without that, I don't think a lot of you can get A for your coursework. So thank you for, doing it, taking the time to do it, and it did reward you well.
Anyway, thanks a lot, Prof.
Oh yes,
Thanks,
I hope
Prof.
you do well also in your final exam, not just depend on that. But those of you who get A, meaning that at least you pass the exam. But the thing is, whether you get A or B, then it depends on you. Because that one, your final exam is 60% of it. So 40%, so siapa-siapa yang get around 38 like that, means you already pass lah,
We'll do our best.
Dah pass lah, tak ada lah lulus bersyarat ke, tak lah kan? But you did pass. But the thing is, takkanlah nak D saja kan? About 40 is about D Kan you all nak yang tu kan? Dengan D plus kot. I don't think so Please do well for the next 60%.
InsyaAllah.
Yes, we'll do our best, Prof. Thanks.
Yes. Okay. Alright, so kita sambung Apart from diffraction dengan interference, where we use crystals, it's possible also we can use light, light as a diffraction grating. Ini dia kita boleh gunakan dengan satu alat yang dipanggil atom interferometer, where actually we use light, laser light, and then we use beam splitter. Sebahagiannya kita transmit, beam splitter ni kita boleh splitkan beam. Kita boleh sebahagian transmit and sebahagian reflected. And then we have another mirror yang reflect it back. And then we have a standing wave, standing wave of light. Standing wave of light ni can act as diffraction grating. Kalau kita pass atoms through it, dia akan scatter the atoms. This is light, that acts as diffraction grating. Selama hari ni, you just see diffraction grating as metals or crystals, isn't it? But we can have light as diffraction grating. And then, we can have our particles and can be scattered by it. And at the end, bila kita use our detector, we can get our diffraction fringes. Here, hasil daripada our particles. But light act as the diffraction grating. Isn't it? Selama hari ni, you learn light as the source, but crystal matter as the grating. But now, we can use light as the grating and matter as the source, and the result is still the same. And we get this vertical fringes because kita punya grating ni macam ini. Just now we get it round because of the crystal. Because crystal kan 3-dimensional, but this one is only 2-dimensional. That's why we get 2-dimensional fringes, vertical ones. So dia bergantung kepada what kind of grating that we use, Then our fringes or our interference fringes, depends on that. Whether we're going to get a round one or parallel bright and dark fringes. Don't you think now that nature is symmetric? We can use matter as the grating and then light as the source. And we can also use light as the grating and matter as the source. And the result is still the same. Tak amazed?
Yes, they are symmetrical.
Yes. Okay, so that's part of kita punya first half, It's about matter waves, Kalau kita tengok, matter waves, we can use electron double slit experiment, we can use Davison gamma electron diffraction experiment, and also atom interferometer. which it will show the same fringes as the one with light. Sama ada kalau light kita guna, we can use it as grating, metal grating, we can get light diffraction fringes, and also light interference by using yang double slit. Actually, what's the difference between interference dengan diffraction? Do you know from your lab experiments? Isn't it look the same to you? Kau ada difference between the two? Tak tahu. Most of you get very high marks for your lab report. What's the difference between interference and diffraction?
Interference is when I think when two diffractions meet.
When two
collide. They collide.
Collide, Diffraction?
So diffraction is one source which is spread out, berkembang.
Okay, spread out after a barrier lah.
Yes.
Okay. Interference, salah tu. Interference is when the fringes tu dia punya intensity is always the same, uniform. Tapi kalau ada diffraction happening with that pada interference tu, the intensity will be different. Yang central will be highly intense, yang the rest it will be less intense.
Okay. I got it.
So dia macam ada envelope. Kalau dia macam ada envelope like that, that shows that diffraction happens. Tapi kalau interference, dia punya intensity semua sama.
Yes, we did that in the lab.
Yes. So that's the difference between interference dengan diffraction effect. Okay. Let's now go to the calculation part of it. Okay, how to calculate the wavelength of metal waves? Okay, what is the wavelength? Kita tengok argument Einstein. What Einstein said? For light in Einstein relativity, E is equals to PC. Kita tahu C, apa hubungan C dengan lambda? Apa hubungan C dengan lambda? What is the relationship between C and lambda? What is the relationship between C and lambda? C is equals to? Macam mana Wait, a lot need to be done for your final exam then. Isn't it? Baru nak selak buku. But never mind, you still have what? 1 month to go? Your exam is what? 1st of June, isn't it? Is it 1st or 2nd?
2nd June.
2nd June. Exactly 1 month to go. Okay. Still have time. If you devote to 12 hours on it, but I don't think you have that kind of time. So E is what? H nu, HF, H nu, and then divide by C. C is equals to F lambda, isn't it? So C over F, so we have it lambda. So we can get lambda is equals to H over P. So macam tu saja. Such a simple kind of argument. Yeah, for light. Yeah, because light, kita tahu light has no mass, isn't it? So E must be equal to PC, isn't it? Actually, apa the equation for E? E for matter. So E is equals to
MC square.
E is equals to MC square. Tu satu equation. Lagi? Selain daripada itu, apa dia equation untuk ni? Macam mana ke? How do I go to that screen? Tak tahulah macam mana to go to that screen, this one. Let me try. Can I get that one? No. Tak ingat lah macam mana to get from one screen to the other. Never mind. I don't know how to get from one screen to the other, so I just write it down then. Remember, E is equals to, kalau kita guna relativistic apa? E is equals to square root of apa? P C squared, isn't it? Plus E 0 kan? Square root. But kita tahu bahawa E0 is equals to okay, E0 is equals to MC squared. Jadi untuk light, M dia is 0, isn't it? So M dia 0, jadi kita dapat E is equals to PC saja. So that's where we get our this one. Kan? Because for light, M is equals to 0. Okay. So we get our inilah PC. And then P, kalau kita terbalikkan, P is equals to H over C. Kita tahu bahawa from photoelectric effect, apa? E is equals to H F kan? Ataupun kadang-kadang dia tulis E is equals to H nu. Nu is equals to F. Samalah. Tengoklah mana satu simbol you guna. Okay. And then kita tahu C is equals to F lambda. C is equals to F lambda. Lambda is equals to C bagi F. So C bagi F is lambda. So kita dapat this expression lah. Ya, jarak gelombang is sama juga dengan Planck constant bahagi dengan momentum. So since kita tahu bahawa nature is symmetric from all that you know just now, so for the Broglie wave, kita just guna lambda is equals to H over P. Yeah, because kita tahu untuk matter, yeah, we have P is equals to mv. Ya, tengok case ya. Kalau macam ini, it means is apa? Case apa? Relativistic ataupun tidak? Kalau kita guna macam ini punya equation, so this one is apa? Case apa ni? Kalau this one is non-relativistic kan? Kan? Tak relativistic. Kalau relativistic punya, E is lambda is equals to H over apa? Momentum kalau relativistic. Kalau E relativistic macam mana? E relativistic, E is equals to E total is equals to apa? Gamma M C squared kan? Dia ada perkataan gamma kan? Jadi macam itu juga kita ada gamma M V, isn't it? Ini case relativistic kan? Biasanya textbook kita kata macam mana? How can we know which one to use what? Ketika mana kita nak guna relativistic, ketika mana kita nak guna non-relativistic ni? Ya, of course kita boleh tengok ketika V is near to C. Tapi kadang-kadang it's not possible for we to know whether this one is V near to C or not. Kita boleh tengok daripada dia punya kinetic energy. If the kinetic energy is greater or comparable to dia punya rest energy, ataupun PC dia is greater or near to rest energy, then kita guna relativistics. Kita kena tengok case PC, ya, kita darab our momentum dengan kita punya C, ataupun kita kena tengok case, ya, H C over lambda. Kan kita replace P dengan kita punya ni de Broglie wavelength. Kalau kita kalikan ini dua, then we see if it's comparable to kita punya E0, then we use relativistic. Ataupun kita tengok dia punya KE, ya, kinetic energy yang kita dapat, is it comparable to kita punya rest energy? If it's comparable, then kita kena guna relativistic. Dia akan larilah sikit dia punya pengiraan. Normally the classical is more than the relativistic values. Okay, jadi kalau dekat exam nanti, don't just use the non-relativistic saja without thinking, ya. You kena check dulu which one to use, and then you tengok yang ini kah ataupun yang ini kah. Alright. Begitu juga masa buat kiraan untuk tenaga, isn't it? You have to look whether you nak guna relativistic kinetic energy kah, you nak guna classical K is equals to half mv squared kah, ataupun K is equals to E tolak E0. Which one to use? Jangan guna classical saja, because setiap kali exam, ya, student just use the classical equation saja, which is wrong, ya. Kena tengok case. Okay, sebagaimana yang saya kata tadi, kita nak prove the Davison and Gamma punya eksperimen. Do you have any question about this one just now? Kan jelas dah, ya? Kalau you tengok dalam example dalam textbook, ada bawa textbook tak? Page 94. Kita tengok example 3.2. Dia tengok dekat solution tu. Apa dia kata? Dia kata relativistic calculation is needed unless PC for the proton is much smaller than the proton rest energy of E0 is equal to 0.938 giga electron volt. Dia kata, kan? So dia check dulu sama ada PC dia is greater than E0 ataupun tidak. Kan? Page 94, example 3.2. So be careful, ya. Don't just use the H bahagi dengan NV untuk lambda. You kena tengok case, ya. Relativistic ataupun tidak. Alright. So basically kita tengoklah, ya, sama ada K tu comparable dengan E0, ataupun kalau diberi lambda, tengok sama ada, ya, dia punya PC tu comparable tak dengan E0. Kalau comparable, then you have to use relativistics. Okay.
Prof.
Yes.
You said comparable means the PC is greater than E0.
Greater ataupun near to E0.
But how much difference can we accept? When we say near.
Near tu tengoklah, kadang-kadang ada case 0.1 pun you dah guna relativistic dah. Kalau the value is very high, kalau in terms of giga ke, kan, mega ke, means it's very high already. Then kalau dia 0.1% pun kadang-kadang kita guna dah terus.
Okay. So if it's greater, we straight away use.
Greater memang straight away use relativistic punya lah. Yes,
okay.
yes.
Sure, thanks.
So be careful about that, yeah, because you jangan just use the classical. Because a lot of students lose marks dalam soalan matter waves ni just because of that. Year in and year out. So that's why I warn you this time round. So that you don't make the same mistake every time. And also untuk case energy, ya. Kalau kita punya soalan relativistic energy tu, there are students yang still use classical K is equals to half mv squared. Yeah, whereas that is the case of relativistics. So salah lah kan, because jawapan tu lari jauh sangat. Tapi kalau case de Broglie waves ni tak lari jauh lah, but still there's substantial values lah, difference dia. Okay, next mari kita proof the wave nature tu. Experiment Davison gamma. Okay, so that's one just now. Okay, so kalau kita lihat di sini ya, remember kita dah belajar dalam 104 apa Bragg's punya diffraction, isn't it? Kan kita dah sampai belajar quite high ya, but this one is still low. Kita dah boleh tahu dengan apa hubungan dia, D dia dengan HKL dengan lattice parameter, but this one is just the simple equation saja. Ya, katakanlah dia punya lattice spacing is D, which is similar to what you have learned before. Ya, but you will know more, isn't it? You know that D, lattice spacing is equals to A bahagi square root of H square plus K square plus L square, the Miller indices kan. But now it's just sini dia bagi D siap-siap ya, the lattice spacing ataupun dia punya interplanar spacing ya. D is equals to 0.09 nanometer. And then kita tahu ya, Bragg condition for in constructive is n lambda is equals to 2D sin theta. Be careful ya, dalam case ini theta now is the theta sebenar dia, bukan theta bagi 2 as what you learn in 104. Careful ya, because this theta is between the incident and the scattered. So dalam case ini is 65 degrees. So apa dia punya lambda for electron? Of course kita masuk saja ya. Our D kita tahu 0.09 nanometer. Our theta is 65. Yes, 65. And kita nak cari lambda. Let's say for the first constructive interference, n is equals to 1. So, kita can get lambda electron. Ya, 2 0.09 times 10 to the power negative 9. Ya, sebab nanometer. Sin because sudut is 65. So, we can get our lambda electron is 1.63 angstrom. Ya? Sebab 10 to the power of negative 10 ya, is angstrom kan. So it's very very small ya? It's about 16 nanometers, 16 nanometers, which is small ya? But still, I mean the devices that we have now, kita boleh nampak dia. Kalau kita guna equation de Broglie pula ya, H divided by P, kita tahu P is equals to mv momentum, K is equals to half mv squared. So what's the relation between KE dengan P? Kita susun semula, so we can get our KE is equals to P squared divided by 2m. So rearrange. Jadi, P is equals to 2m KE. Kita tahu our punya case, our accelerating voltage is 54. So, the kinetic energy is 54 EV lah. So, kalau bubuh dalam ni, so we still get our lebih kurang 16 nanometer juga. So, nampak sama saja, equivalent ya, lebih kurang daripada eksperimen and also daripada kiraan de Broglie. So this experiment indeed ya, proof apa yang disebut oleh de Broglie. That's why he gets the Nobel Prize. Jadi kita boleh kata moving particle with momentum mv, yep, dia ada wave function being associated with it, psi, where psi squared is the probability of finding the particle. The wavelength is being given by h divided by p. It's actually the group wavelength. The group wavelength of this wave function is h over p. Dia bukan the phase velocity, dia bukan. Untuk group itu. Okay, let's try to solve a few. Okay, kita tahu untuk case non-relativistic, kita cuba dapatkan lambda for this car. Let's say the car is 1000 kg. The V is 100 meter per second. Lambda for the car berapa? Kita cuba kira. Lambda de Broglie for the car is berapa? H divided by mv. H is equals to berapa? 6.63 times 10 to the power of negative 34. Patutnya by now dah hafal dah. Tak payah tengok pun dekat table of constant, isn't it? Kau dah banyak kali guna lah kan.
Dalam final bagi tak?
Final bagi, tapi biasanya tak ingat dah. 6.63 times 10 to the power negative 34. Banyak kali guna dah kan. Nanti dekat dalam atom, when you learn pasal atom, Bohr atom semua tu, H tu kita guna lagi kan. Patutnya boleh hafal dah lah kan. Biasanya saya bagi. Okay, so berapa dapat untuk K? Kita tahu ini bukan case relativistic kan, because dia tak sampai pun. Tak near pun the speed of light. So kita boleh gunalah H divided by mv. So berapa dapat? Selva? Dapat berapa?
6.63 times 10 the power of negative 39.
Aha, ya betul lah tu. Kan? It's very very small, isn't it? Tak visible pun for our eyes kan? Ada alat yang boleh tengok apa benda tu, isn't it? So let's go for dust particle pula. So how much is it? So Ain dapat berapa Ain? Ya Hafiz? How much did you get? Okay, so dapat berapa?
6.63 times 10 to the power of negative 24.
23. Okay. Kecil kan? That's why kita tak nampak. Isn't it? Tapi kalau benda tu smaller, elektron semua tu, we are able to see it because dia punya wavelength is much bigger. So that's why it's not visible to our eyes lah ya. Because it's very small. Now let's masa dah tinggal short. No, start. Now I would like to show you satu case ya. Okay, kita tengok this one. Diameter of nucleus is about 10 femtometer. Yeah? Femto tu 1 times 10 to the power negative 15. What is the kinetic energy in mega electron volt of a proton with a de Broglie wavelength of 10 femtometer? Jadi case ini, kalau kita guna classical, kita will get a bit different jawapan than kalau kita buat dengan relativistic. Tapi untuk case ini sebenarnya kita kena guna apa? Is it relativistic ke ataupun non-relativistic? Katalah dia punya E0 is actually 0.938 giga electron volt. Sebagaimana yang saya kata tadi, you kena get the PC value of the PC dia. Jadi kalau value PC dia comparable to dia punya E0, then you have to use relativistic, isn't it? Because masa dah tak cukup, I just show you. Kalau kita guna non-relativistic, so this, kita akan dapat 8.23 mega electron volt, ya. Tapi kalau kita guna relativistic, kita akan dapat 8 mega electron volt. So yang mana satu kita nak guna ni? Yes, sebab kalau kita tengok PC dia ni is comparable to ini, isn't it? Ni 0.124 giga electron volt PC dia. Jadi E0 dia is about 0.9. So dia comparable, isn't it? Lebih kurang. So kiranya jawapan is 8. So jawapan dia, kita kena ambil this jawapan. So this is the jawapan sebenarnya. You have to take this one. Ya, sebab ini PC dia, macam saya sebut tadi, is comparable to this one. Kan? So we have to use this equation. Ya, kita tak boleh guna equation ini. Disebabkan oleh this condition. Okay. So, kita have to use this one to get this value. Kan saya kata tadi? So, ini lebih daripada ini. Tapi, jawapan dia sebenarnya adalah 8 mega electron volts. So, hati-hati ya. Okay, do you have any questions setakat ini? So, this is our last video conference ya for this sidang. Okay, soalan final exam will be similar to your soalan berterusan. Macam tu lah ya. The first soalan, you mesti bagi comment and what not. Ya, based on the physics principle lah ya. And then dia ada kiraan-kiraan adalah ya. InsyaAllah you can do it.
Berapa soalan?
Oh, saya pun tak ingat. Saya rasa 6 rasanya. 6 pilih 5 macam tu. Kalau tidak pun 5. Mesti jawab 5.
Prof, ada choice.
Itulah saya dah tak ingat. Saya dah lupa dah. Kalau 104 saya ingat memang ada choice. Yang ini saya tak berapa ingat sangat.
Yang chapter 4 ada masuk juga.
Chapter 4 tu yang mana? Yang atom
Yes.
Yes, of course ada. Satu soalan mesti daripada situ. Satu soalan daripada relativistic, satu soalan daripada particle nature, satu soalan daripada wave nature, satu soalan daripada atom, satu soalan yang tanya semua. So mesti ada punya, jangan tak baca. Okay.
Yang atom tu ada kira-kira tak?
I think so. Mesti ada lah kan. Mana ada fizik tak ada kiraan. Kecuali soalan nombor 1 saja. Kalau tak silap saya tak ada kiraan. Yang tu memang soalan you have to explain ya, and comment. Kalau nak suruh lukis graf ke, guna equation ke, something like that. Soalan nombor 1. Okay. Biasa soalan nombor 1, student jarak jauh tak ada masalah. Because you all banyak pengalaman You can write based on your pengalaman physics principles. Okay, all the best then. For the 2nd of June. Jangan gabra-gabra. InsyaAllah you all can do it. Okay, all the best.
Thanks a lot. Masa exam Prof juga.
Ha?
Prof jaga masa exam nanti.
I know. I won't be around because saya ada meeting kat KL dekat Putrajaya. So I won't be, tak jagalah. Lagipun yang lain pun saya tak jaga juga kan, isn't it? Oh, nak tengok muka saya juga Tak apa, saya doa you all sementara buat exam tu. So that Allah make it easy for all of you. Okay.
Yang formula yang complicated tu ada bagi tak?
Oi, mana ada bagi formula? Tak ada. Kita bukan macam SPM STPM bagi formula. Kalau universiti tak ada dah. Kecuali statistical formula dalam maths, statistik saja. Yang lain fizik memang tak bagi formula dah. Sad to say lah Hafiz Tapi tak apa, ini last you punya physics course kan? Tak usah takut lah. Kalau dah selalu buat penyelesaian, the equation tu will come secara natural to you. Okay, all the best then.
Thanks a lot for your guidance, Prof.
Other questions about the topic? Conceptually, it's very confusing. So, before we go into solving exact questions, I want to make sure that you know what is a conceptual problem that you can understand. Then I explain to you. It's very interesting.
Maybe we can start with the beginning first. Don't be scared.
So the question is, I think the issue is this. We know very common knowledge. We have very common knowledge about light. We know what light is. We think light is like a wave.
Sometimes say particle.
So we always think that light is a wave. So you agree with that? So then you try to recall what you mean by that statement. So when you talk about that, it means the light behaves like a wave. So you expect that when light when it moves like a wave. Actually, it's not moving like a wave, but its behavior is not displayed by a particle. Particle won't behave like a wave. So for example, wave, it moves in a straight line, and then wave will display so-called diffraction pattern. Right? So particle wouldn't display diffraction pattern. If you say you roll a bead, or it just goes straight. So when it hits on the wall, then it hits on the wall. So let's say if you put a lot of balls that is going through walls, all the beads will either go through or it doesn't go through. They'll go through. Right? And go through or it doesn't go through. But then if it's a wave, then it's a different story. If it's a wave, then when it goes past through this light, it doesn't go through. It will actually diffract. Right? So light is very different from particles. So what light, when it goes through a small hole, it will diffract, and then it will interfere. So this is the basic notion about light as a wave. So I assume that when we talk about this, then we always know what wave is like, behave like a wave. So we need to be very specific to describe the difference between a wave and a particles. Wave have properties. Wave is not a particle. Wave is a phenomena. Wave is not a particle. So if you have a bead say a bead made of glass and a wave, of course these two are totally different things. You don't expect a bead would behave like a wave. It doesn't make sense at all. Okay, so first of all, you have to make a very clear distinction that there is this incompatibility between a wave and particles. So specifically particles, it has this property which is not shared by wave. So for example, a particle is placed here, is all lumped. People call it localized. A particle is strongly localized. If a particle is located here, it will not be able to find it elsewhere. So this is common sense about particle. So it's what we call localized, and it's like a mass concentrated in one place. It cannot be simultaneously found at other places at the same time. Right? But wave is different. When I speak, you can hear me because mine was
frequency.
You have to be very specific about this. You cannot just say frequency. This is a phenomena. A phenomena is like this.
It's like how you say it spreads out.
Yeah. So why can you listen to me at the same time, and you also can listen to me at the same time? Because my voice, which is spread in the form of wave, it's spread out and fill up the whole room at the same time. So it is fair to say that my wave from the mouth goes to my ear and goes to your ear at the same place at different time, at the same time at different place, because wave can be spread out in space. So this is a totally different idea than a light particles. If I use a bullet, I shoot you, and if you get a bullet, then you will not be straight sharp. You cannot have a bullet that will hit two people at the same time. It never happens. But wave can. So wave spread out in the space. So you cannot reconcile the pictures of a wave and the particles. And we always think that wave behave like light behave like a wave. Specifically, light would actually undergo what we call a diffraction pattern or interference pattern. Just like when the light goes through two small holes, when you shine a light on it, then you see spectral that looks like this. And it's a light which is spread beyond its shadows. So this is a shadow. So let's say if this is a wall, then you shine a light, then this is the shadow. So these are the shadows. So if light will behave like particles, when you shine light, then you won't see anything beyond the shadow. But the fact is not true. The fact is that you always see a spread. You always see a spread of light beyond the shadow. We call this a diffraction. So let's say if we have 2 points of wave that goes through 2 holes, then these 2 holes will actually undergo interference pattern. So interference pattern. So light will display this interference pattern like water. So you see water, they have this interference where you have this mutual enhancement and yeah. So this is what we call wave phenomena. And then another very important characteristic about wave is that the energy spread out. The energy spread out, and it's like the wave has energy. Somehow the wave has energy carried along it. Then when wave is moving and spreading, you can imagine that the energy gets spread out. But if you throw a ball, then the ball will move in the direction, and all the energy are concentrated and moving along with the ball. Right? So it's like a bullet that hits you, it will never hit other people. But wave is not. Wave can hit you and hit you anywhere. So the characteristics here is the energy of wave sort of like spread out. And another very important thing is that when you spread out, the energy of the wave is said to be continuous. Whereas the energy in the particle is discrete. It's sort of like energy are all contained inside, and it will not spread out in space. But in wave, the energy is sort of like spread out and it's continuous. Everywhere you find at this point, energy are all can be found. So this is a very sharp distinction between a wave and a particles, especially if you like it's like you have water. The water you fill it up, so the pipe fill up a tank of water, then the water will get accumulated and then will fill up gradually. So the filling up process is a gradual process which is continuous. The other way of filling up things is like you, instead of water, you say you have a lot of bits, small bits. So bakuli yang kecil-kecil, then you put in one by one. You put in one by one. So every time you put in one small bakuli. So this is like you fill up the thing discretely, whereas this you fill up and then the tank we call it continuously. Continuous. So this is like what the energy carried by the wave, which is filling up things continuously, whereas this is like discrete energy. So you throw a ball in it, then you have this much. You throw another ball, you have this. So every time you throw one. So this is discrete. This is continuous. So I will make sure that you understand what we mean by discrete and continuous. So continuous, like when you finish, then you one lump, you throw in, then you have to throw another time. So all these are individual. Yeah. So this is discrete. This discrete. This is continuous. So energy carried by the wave is continuous, whereas energy carried by particles is discrete. Right? So that means that if you have okay, let's say you have a patong here, somewhere patong. then you want to knock down the bottle. So you throw a ball. If the ball is hard enough, then you hit it and you jatuh. If you throw it not hard enough, then you will not jatuh. So you are like throwing energy to a bottle discretely. So either the energy is enough to overthrow the bottle, or it will not. So another thing is that you try to spray it. You try to spray with water. So you try to spray with water. So water carry energy as well. And so water, if the water is not strong enough, you will never be able to overthrow it. Okay. I will try to give you some analogy.
The water spray the surroundings.
Okay, so then you try to compare this scenario and this scenario. So the water, since it's coming in continuously, so you can fill up the tank gradually until it overflows. So in this case, what's the difference between this and this? In this case, since energy is coming in, so it actually flows. That means the water supply can be accumulated. So you switch on the tap, then you wait. Then maybe 1 second, maybe 5 seconds later, only then the water can fill up. Okay. So water you get filled up, and then you can accumulate the energy. So this is only possible if the energy flows in continuously. So how? Okay. So this has to do with your questions. You say this. You say, imagine that you have a plate, a metal plate, where it has an energy. Where this energy has the particles. The particles somehow has a string attached to it, and this particles is called electron. Is bound to the surface by a string, and the string has a strength. So you want to kick out the electron from the surface. So obviously you need to provide enough energy to break the string. So this is like throwing a stone. You throw a stone in, either you can able to kick it out, or you don't. If your energy is not enough, you will not be able to kick it out. Okay. So there is a minimum amount of energy that is required to kick out the electron. But so you try to kick out the electrons by providing energy to the surface. So then it depends on how you provide the energy to kick out the electron. There are two ways. One way is by throwing stone on it. The other way is by filling up the energy, like water flow into from a hose and fill up the gap gradually. So there are two ways how you provide energy to kick out the electron. One is to throw in the energy continuously and let it accumulate. So there may be, say for example, some minimum amount of energy required to throw it up. So either you fill up at some rate, some supply of energy, you wait for a while for, let's say, some time delta T. So that when you wait for long enough, then enough energy is accumulated so that the electron that has enough energy would be kicked out. Or the other way is you throw a stone which is strong enough that it's able to break the electron from it. Now from physics point of view, both methods, either you throw a stone to kick it out or to fill up the electron energy, are similar in effect. It should be like, because why? Because if you shine this with wave, then wave deliver energy continuously, as I said. So if the wave has not enough energy, then you just have to wait. You just have to wait the ball because it fill up the tank gradually. So when you wait long enough, then the energy will be enough to be filled up. Then you will kick out the electron. It's just a matter of time to wait for the energy delivered to the electron.
Because it's continuous, so
yes.
it's like gradually from small become bigger.
Yeah. So when it become bigger, the energy. So what is important here is you need to wait for a little while. It will not. The electron will not be kicked up instantaneously because you have to wait for the water to fill up. Once the water fill up, then the electron, enough energy is deposited the electron will kick out. So the other way is that you're going to do this. You throw a ball in it, and immediately if the energy is large enough to break the electron, then it will kick out.
Can it be discrete?
Yeah, it will be discrete. Okay, so now the question is, you think the light is continuous wave? Light is continuous like a wave. So wave should deliver energy continuously. So no matter how strong is your energy, so if you say you have a light could be have a strong light or weak light. So if you say you buy a very powerful light source, then it's very bright light. Then if the battery run out, then it become very dim. So dim light has low energy. Strong light has very powerful energy. So if you use a strong light to shine on the surface, you expect the electron to kick out very fast. If you shine it with a light, then dim light, then the electron should be also be kicked out.
But take the time.
Yeah, that's what you think. So as long as it's a light that delivers enough energy, then electron will be always kicked out, no matter what surface it is. So you shine a light on it, then you wait, then you expect electron to be kicked out. There should be no threshold. No matter how strong the light that you use, it could be strong one or weak one, electron will always be kicked out. So that's why we say that there's no minimum intensity in the light to release the electron. You can have a low intensity or high intensity, electron will always be kicked out. It's just like you go to McDonald's, you want to buy a Big Mac. Whether you are 3-year-old kids or you are 80-year-old person, you always can buy a McDonald's. So there's no limit, right? So it's just that it's just that old people walk slower, and young people walk faster. So you
take time.
Yeah, it takes time. So it's a matter of time if light were to deliver energy. But if you throw an electron, if you throw it with a stone onto the surface, if the energy of the surface is strong enough, stronger than the spring's energy, then electron will be kicked out. And if the stone is not strong enough, then electron will not be kicked out, because stone energy cannot be accumulated. When you finish throwing, either you have enough energy to kick out or you don't. So you throw a stone, you wait. Either you kick out or you don't. You don't need to wait. So immediately, if you have energy enough in your stone, you throw it strong enough, then the electron will be released instantaneously. Right? Okay, so these are the general argument. This is what we expect to the surface electron if you were to kick out the electron from the surface. So what people did is that say, okay, now light is an electron. Light is a wave. So when I shine a light on the wave, I shine a light on the surface, I will always have electron kick out, no matter what, no matter how long I wait. Okay. But then they don't see this. They see something which is very weird. They see three very important behaviors of light. That is, when they shine light, they can use. So they use red light. Red light. Red light has a wavelength which is long. Red light has a long wavelength. So you have to understand this light comes in different color. The long red color until the purple color. So the purple color is a light which has a shorter wavelength. So red color light has a longer wavelength. So if you have a same color of light, that means you have the same color of wavelength. So now imagine this experiment. You take a light, say a red color light, you shine it onto the surface. Then you can shine it with a very high intensity or low intensity. Then you expect that if you shine it with very, very strong intensity with the same red light, you expect electron to kick out fast. Red light is dim, but the same wavelength, you just put it a little bit longer. If you use a purple color light, you expect the same thing. You shine it with a purple color light. Intensity strong one, your electron will kick out immediately or very fast. Right? But what they find is the opposite. They don't find this. They find that the electron will be kicked out from surface no matter how strong is or how weak is the purple light. So as long as the purple light, as long as the purple light, the wavelength is the same. No matter how weak it is, how strong it is, the intensity, electron will always kick out.
So it depends on the time?
It doesn't depend on time. There is second characteristics. There are three characteristics about this experiment. So you use same kind of, I need to write. So these are these experiments inside. So they shine with wavelength. Then what they do is they find that electron will be either kicked out. There will be electron kicked out as long as the wavelength is less than certain number, no matter how strong is the intensity. So in physics, in more practical, what it means is you shine it with a very, very intense light. So let's say you have a wavelength, say a purple color light. So the purple color light has a wavelength which is very short. I think purple color light is I think 400 nanometer. Then you have a red color light. This is purple. Red color one, I think is 700 nanometer wavelength. So then this lambda will be some number. It will be like, I think, say 500 nanometer. So they found that if you use a wave which has a wavelength less than 500, such as the purple color wave, then when you shine on the surface, no matter how strong or how weak your intensity of light is, electron always get kicked out. But then if your wavelength that you use a red color light, you have a wavelength of 700, which is larger than the threshold, then when you shine this wavelength with a very, very strong intensity, much stronger than this one, electron will not kick out. No matter how long you wait, no matter how strong the intensity you use, electron will never kick out. This is what they found.
But actually, if like from what you have explained, it should kick out.
Yes, it should kick out. You should expect when you say you should kick out, because if light behave like a wave, the energy will get accumulated, just like water fill up the tank. And then there is a lack of time. But what they found is that only when wavelength less than certain threshold, it will get kicked out. And the second phenomenon is, you see the first phenomenon is the existence of a cut-off wavelength. Below the cut-off wavelength, light will be kicked out, electron will kick out. If you use a light which has a wavelength larger than the cut-off, then the electron will not be kicked out. The second phenomenon is that when they do the experiment, they measure the electron instantaneously without waiting. So for example, you use a very, very weak intensity light, very, very weak intensity purple color light. No matter how weak it is, as long as it shines, immediately electron get kicked out. So these are the two.
Dia ada certain benda ke yang macam work function, they use whether the zinc or sulfur or calcium to sodium to break up the electron band.
So you salah tanya surface ini lah. So what are the surface? So you tukar surface dengan you ada aluminium surface, ada lithium surface. So this is come as a third characteristic. So for this experiment, there are three characteristics. First is the existence of the cut-off wavelength. Second is that the electron get kicked out immediately. Third meaning is that if you use a different material, plate, the cut-off wavelength will change. So this is a phenomena that people observe. So from this phenomena, this experiment, you have a lot of controversy because light behave like this, it should not behave like this. Like if you compare it with throwing the electron with a stone, then the experiment result seems to agree better. So you have a wavelength which is less than cut-off. Then that means it is like you have a stone that has energy strong enough to kick out the electron. If you use a wavelength which is larger than the cutoff, it's like you throw the electron with with energy not enough to break the spring. And then if it's a stone, when you kick out the electron, it will be kicked out immediately. The stone will not need you to wait because it doesn't need like water to fill up, take time to fill up. Electron will just deliver electron energy immediately. So this experiment, it makes you feel like as though the light does not behave like what is predicted if it were a wave. It's more like a particle behavior. It delivers electron energy instantaneously, and then it will either kick out or you don't.
Okay.
And then no matter how long you wait, the energy will just not get accumulated. So that this is the first piece of evidence, 1904. I think 1900, 1904, during that time, people carried out these experiments, and then they cannot find an explanation.
Conclusion.
They cannot find because the experiments show a very sharp controversy as though it's a sharp controversy because you don't expect the light to behave like that, because you expect light is like a wave. But light being a wave, it cannot be explained. It cannot even be used to explain this experiment. So people got into controversy. So then someone came up with explanations, 1905, and then he solved this problem by giving some propositions, and then he got a Nobel Prize for that, 1905. It's called the photoelectric effect.
Oh.
Yeah. So first I have to understand what you mean by photoelectric effect. So photoelectric effect is this effect that I mentioned just now. So now you should be able to understand what you meant by photoelectric. It's experimental finding. So exists a threshold, and then no matter how long, no matter how strong is the intensity, the threshold. So normally these three experiments, these three phenomena, 1, 2, 3 characteristics, is summarized into graph. Into 3 graphs. I think the first graph is the existence of a threshold. Then we need to understand the experiment, how they carry out the experiments. So what they do is they have a metal plate. I think they have a plate, right? So then they shine a light on it with a wavelength. Then on this part, they expose this to a positive state. Means exposed to negative, positive. Okay, so this is the tube. So what they do is they shine a wavelength. Then I think then the electron will kick out. This is negative. I think. So somehow there is this current flow in the direction of how to draw this. I think I'm going to draw this now. So the idea is electron will get kicked out from the surface if wavelength is short enough. Then the electron gets kicked out. It will travel because of the heat. It will travel again in this direction. So we can measure the electron. The electron will be measured from this side to this side. So what you do is you try to, because electron will move, right? So electron will move with some kinetic energy. Then say if this is negative, so if this is connected to negative, then electron, okay, let's say if this is a low battery. So electron that is being kicked out will travel towards here. Then you will measure the current. So what they do is they measure the current. For different wavelengths. So they find that when the wavelength is less than some cutoff, you got some current. But when wavelength is larger than some cutoff, there's no current. It just means that when wavelength is smaller, then the current will flow. And if wavelength is larger, then the current will not flow. That's what it basically says.
So if the wavelength should be smaller than the current.
No. I think as long as electron are kicked out, then current will flow.
Electron have kick out juga kan? Dia akan terbebas juga.
Asalkan dia punya tenaga cukup, dia akan tenaga luar. Asalkan dia punya tenaga cukup, dia akan tenaga luar electron. So if you have a current flowing. Okay, so then what you want to do is to be more specific. You want to measure if the electron is kicked out, what is the kinetic energy of the electron? So it's like this. So if you have electron attached to it, then it's attached to it with a spring. So to break the spring, you have to pay the penalty, because it's like you want to jump out from the gravity on the surface. You jump, and to jump hard enough, or else you will not be able to live. Right. So it's like electron, in order to leave the surface, we have to have enough energy for it to kick out. Okay, so imagine that the light deliver the energy of this much. Then some penalty has to be paid for this electron to get rid from the surface. So that means your energy has to be larger than the penalty before you can kick out the electron. So if the energy is larger than the penalty, then the electron will be kicked out. So the energy that you pump in to kick out the electron is related by this. You put in that amount of energy by wave, by the light, then the electron that's kicked out will move. Electron that move has energy. We call this a kinetic energy. Yeah, last 2 weeks we mentioned any particle that is moving will have energy. We call it kinetic energy. So this kinetic energy is the difference between this one and this one. Yeah, I think it's just like you have say for the kids, then your father gives $10. Then he get the money, he wants to go to the school. So you have to pay the ticket for the bus. The bus is $1. So you have to pay $1, then when you go to school, you have to pay $9. So you expect that the kinetic energy from that we measure from the surface would be a difference between the energy provided and the penalty that is used to buy the electron. So you have this very simple relationship. You measure the kinetic energy here. You can measure the kinetic energy. The kinetic energy is measured like this. If you impose a potential between them, this potential is a battery. You can tune the battery to make it larger or smaller. The potential can be 1.5 volt, 7.5 volt. So what you do is you try to tune the voltage such that when the voltage is the same, if the voltage times the charge is the same as the kinetic energy of the electron, then the electron will not be able to reach here. So electron gets kicked out, it will move from kinetic energy, but this voltage will try to oppose its motion. So if the voltage is strong enough, then electron will never make it way to the other side to complete the current. So this is how people do the measurement. They want to measure the kinetic energy of the electron to kick out from the surface. So what they do is they impose a voltage between these two, and then they tune the voltage such a way that they want to know what is the voltage where the electron will never reach there. If the voltage is small, then the electron will reach there. If the voltage is just nice enough, then no electron will be able to reach there. So then the electron will just halt and then no more current. So people, by tuning this voltage until no current flows, then they will be able to know what is the kinetic energy of the electron. So basically, you perform this experiment, then you impose a voltage, then you tune it until you don't find any current. That allows you to measure the kinetic energy of the electron. So they find that the kinetic energy of the electron can be measured using this method. Then they find that the kinetic energy, according to this argument, that the energy delivered to kick out the electron have to obey this relationship. So the kinetic energy of the electron will be the difference between the energy that comes from the light minus away the penalty for the electron to leave the surface. So these two relationship. So this is what you measure from the experiment. This is what assume this from conservation of energy. So what they found is that the kinetic energy that they measure do not depend on the intensity of light. Right? The light, no matter how intense it is, it can be very, very long, very, very intense, but the kinetic energy that we measure always the same. So you have this graph. The graph looks like, I think this is the graph. The graph on this figure 2.10. That is, no matter, I think the graph looks like this. That is, no matter what the intensity is, this is I think I naught, 2 I naught, 3 I naught, if the intensity is very large, then the potential, the stopping potential that you measure is always the same. So this graph, it carries the information that no matter how strong you shine a light on it, the kinetic energy of the electron will still remain the same. But this is a controversy because you expect the stronger the intensity of light,
higher the apa? Dia punya word tu.
Yeah, you expect that. You expect jika you pakai intensity yang lebih besar, lebih kuat punya cahaya, kuat in the sense that dia lebih cerah, lebih terang, keamatannya lebih tinggi. Jika you pakai light dengan keamatan yang sangat tinggi, you expect elektron punya kinetic energy akan tambah. But you don't find it. You find the opposite. You find it's always the same.
Always same.
Yeah. So this is puzzling, and then if your wavelength, if your wavelength, this is for wavelength less than cutoff. But if your wavelength is more than cutoff, if the wavelength is more than cutoff, you get nothing. If the wavelength is more than cutoff, you get nothing. You don't measure any electron. You don't have kinetic energy at all. You don't have current flow at all. So, and then as long as your wavelength is less than cutoff, no matter how small your intensity is, you always have the electron pick up, and the kinetic energy of the electron is always the same. Okay, so this is one of the examples that shows that your electrons is hit up by light, as though the light is not a wave. Light behaves more like particle in this sense. So this is total electricity. Okay, so I think the idea is like this. So then if we go to the next bit, is about not too much about the physics, it's about formula. You need two formulas for this total electricity. One formula is like this. That is the formula for the electron voltage is the total energy of wave Gaussian minus the work function. W is the work function. You have, let's say you have a surface one, electron that have to pick up have to pay the penalty of Q1. If you have a different surface, then you have to pay another voltage. It's just like this is the this is the toll number 1. Then for toll number 1, you pay $1. For second type of toll, say in KL, you have to pay $2 toll. So different surface is like different toll, you have to pay different penalty. So you expect that if you shine the same light, for example, shine the same wavelength of light onto different surface, the kinetic energy will be different because the kinetic energy is the difference between the wave and the wave function. So if you shine the same light with the same energy on the different surface have different tone, therefore the kinetic energy of the electron will be different. So we have this one formula, then we have another formula which is most important. That is the energy of the light. The energy of the light is given by this H over lambda. So which shows if you shine a light with a wavelength lambda, then the light carries energy, and the energy of light is given by H over lambda. Now this formula is a very, very weird formula, which is not in existence at all before 1900. So this formula, it relates the energy of a light to its wavelength. And this is
H is height, is it?
H is a constant. It's just a constant.
Yeah,
Planck constant.
Planck constant.
No, we call Planck constant. Planck constant.
Planck.
So this formula it actually refers that the energy of the electron behaves like it's a discrete particles. The light behave like a particles. The energy carried by the light is as though the light is a stone which has a discrete energy.
But light should have continuous energy.
Yes, this is what you think. Light should have continuous energy. It should not behave like a stone that carries discrete energy. But in this case, in order to explain the photoelectricity effect, you have to explain the photoelectricity effect by assuming the light to have discrete energy like a stone. And the discrete energy of a light is related to its wavelength. So this relationship between the energy of the light and the wavelength is a very weird one. And it only exists in 1900. It actually is proposed in another experiment called Planck experiment. You just accept that light carries energy given by h over lambda. H is a constant. And this is a formula that relates the energy of the light to the wavelength of the light. So then you have this formula. Then it explains the fact that different surface have different wavelength. So I think what else formula do different formula, and sometimes because the light right is moving with the speed of light c, and then it has a wavelength of lambda. And light will also have a frequency. So the relationship between the light speed and the wavelength and the frequency is given by another formula. C equals to f lambda. So this is the relationship that you should memorize. It relates the speed of light to the frequency and the wavelength. And the speed of light is a constant. So you can also write this formula as C over F. Sometimes the F is written as mu. H mu over C. So I think some H over lambda. And then lambda is C over mu. So energy is related to the frequency or is related to the wavelength for light. So we have these two equations. Then there's third equations that we have to write down. It is the work function. The work functions. I think that's all we need. So we combine these two equations. Then we have this equation called h mu over c is equal to E lambda. And then E lambda is EV plus sigma. EV, and EV is just your kinetic energy. Okay, EV is the kinetic energy of the electron plus the work function and h mu over c. So you have this formula that looks like this. So you have this formula. So this formula is, so what I have done is I just have combined this formula with this formula. These two are two different formula. And then I also make use of the fact that frequency and wavelength and speed of light is related by this. So then I'll just divide it, then I've got these equations. Now this equation is what we have found in 2.8. So when you look at the equations in physics, you don't just remember or memorize it. You try to understand what each term means. So this term means this you have an experiment, you have a surface, you have a light that comes in. Then when light hits on the surface, electron will get kicked out, and then you can measure the electron kinetic energy. And the surface has a work function that would bind the electron to it. Okay, so what this means is that you plot Ke equals to H nu over C minus W. Okay, so what you do is this: you carry out experiments. So lambda is wavelength. So lambda is related to the wavelength through C over nu. Okay, so you use a frequency, a fixed frequency or fixed wavelength is the same. So you shine the surface with a fixed frequency of light. Then you measure the kinetic energy. So this is what you do in experiment. You shine a light with a given frequency, say 1000. Then you measure the kinetic energy using the method I mentioned, the potential method. So imagine that this is what you measure. You have kinetic energy, then you have a frequency. So you fix the frequency, then you measure the kinetic energy, then you get one data point. Then you carry out the experiment again by changing another light. So you shine it, you say the purple color light, and you use a different blue color light. Then you have a different one. Then you carry out another experiment, so then you find that you carry out this experiment, the experiment gives you a straight line. And then this straight line can be just explained by this formula. That is, when you fix the frequency like this, kinetic energy versus omega. So you find that the graph looks like this. So in this experiment,
lab. Single slit and double slit.
No, this is not. This experiment, you measure the frequency and kinetic energy. Then you find that the graph would be like this. But this graph is described by this formula. This is the y, this is the x, and this nu is sorry, this is not the this is our frequency. It's called frequency. So the slope of the frequency is h over c, the slope. And then at this particular point, the kinetic energy becomes 0. It is when h equals to some fixed frequency, then the kinetic energy becomes 0. And you cannot measure anymore. There's no, because electron has no kinetic energy. So you carry out this electron experiment like this, and you draw a line. And this straight line of experiment is well described by this formula. So you can then explain why there exists a threshold frequency. That is, when the frequency is less than, if the frequency is more than this one, then only electron will leak out. If the frequency is less than this threshold, then no electron will leak out because electronic kinetic energy cannot be negative. So that explains the existence of a cutoff, because the existence of a cutoff, like I just write like this. So this is the same as C over new cutoff. So the cutoff in the wavelength is the same as the cutoff in the frequency. So the cutoff of frequency is opposite. Say the wavelength has to be larger, has to be smaller than the cutoff. Only then you see it. Equally, you say the frequency has to be larger than the cutoff. Only then you have electron leak out. So this graph, this formula explains very well the photoelectric effect. And when you when you do this experiment, when you do this equation, it doesn't involve intensity. So that explains the experiment. So I was telling you about all this controversy of the light and whatever, and this controversy in exposure experiment, photoelectricity experiment. So the solution in that is in these equations. So this equation explains the photoelectricity effect completely. The thing that you need to realize is when you write down this equation to explain the photoelectricity effect, you assume the energy of the photon is given by this formula. And when you do this, you are already giving up assuming light as a wave. Yeah. So this assumed light now behave like particles. If you give up the light as a wave interpretation, then everything is explained totally well, and you do not need to wait for electrons to be kicked out. It will kick out immediately because now I'm going to give a light. And then you can also explain the existence of a cutoff frequency. So this formula explains the cutoff frequency, that existence of cutoff frequency. As long as the frequency is larger than the cutoff, you always see a photoelectricity. If it's less, then you don't see it. So you explain this photoelectricity experiment at the expense of giving up light as a wave. So that is what the photoelectricity is. This is a cutoff. But this
here, they give KE max. Do we need to write in the exam like max or
Kelas kita ni. Even like why is K minus J is slightly more than because electron has traveled.
So the formula is the maximum photo electron energy.
Yeah, because the electron kinetic energy that
KE max.
The potential, the kinetic energy is more than W because electron they come from below. It's not on the surface. They come from below. It takes extra energy to travel. So that means it needs more energy to refer to it like the penalty paid by electron on the surface to release. But if you have electron at the bottom,
it needs more than the one in the surface.
Yeah. So the electron kinetic energy that leaves the surface would be in general less than what is predicted. So the maximum one will be electron from the surface. The electron from the surface will be have the most largest maximum, have the largest kinetic energy. Electron that's coming from the bottom of the surface will have a pretty larger energy. So that finished the part of photoelectricity effect. So, let's see, it talks about light behaving like wave. So these are all properties of wave. Yeah.
nampak.
So when you read the books, the book comes in sections. So each section has a meaning. So as long as you know enough, that means you know enough. Yeah, the concept. So this is the concept. So for example, it shows you this picture of this car picture. The purpose of the discussion in this picture is just to make you aware of the nature. Yeah. So wave behaves like this interference. Particle don't, and wave takes time to deliver energy.
Monochromatic light source means monochromatic means one, is it?
One wavelength.
One wavelength.
No, it means the wavelength is
monochromatic.
It means the wavelength.
One source.
One source. No, it should be more specific than that. It should be that the light that comes from the source has only single wavelength.
Single
wavelength. Like light from this source is not monochromatic. It comes in different wavelength.
So let's say if you like how we did the experiment in the lab with single slit and double slit, so there is light coming, right?
Yeah.
So that is called mono.
No, the monochromatic has nothing to do with the numbers of slide. It has to do with the light source. This light source is not monochromatic because mental is not monochromatic. Because the light source will emit up with various wavelengths.
Only what is monochromatic?
That means the light source gives out only light that has only a sharp wavelength. Say the light.
Laser.
Yeah, laser.
The
other good experiment would be the natrium light. The natrium light wavelength is very sharp. It has only one or two wavelengths. I think 400 something, 355 nanometer, and we don't have other wavelengths. So most of the light that we see in our daily life are not monochromatic, including your light source, white source, your torchlight. But laser light, these are monochromatic wavelengths. Very little time we see monochromatic light. But in experiment, you can have this monochromatic light. One way is to use a natrium light. Natrium, but these are wave source, light source that has,
which is monochromatic.
Yeah, more approximately, because the wavelength is sharp. It's not like very diffuse. The light from the sun appears like white because it's a mixture of wavelength. So when you mix up, then it becomes like white color. So the natrium light looks like yellowish because the light source has a wavelength that falls into the color of orange. It has no wavelength on other wavelength. So light source of LED also is monochromatic, more or less. So you have a LED light.
LED
bulb. Not white color one, the blue color one, red color one. You have red color LED. So it appears red because the light that comes out from it have only red
same color.
When they say same color, it means the same wavelength.
Okay.
So this is finished with the photoelectricity effect. But this is only one experimental evidence that hinted on the fact that light do not behave like wave as we expect.
Yeah.
There are other experiments that also hint on this. The other experiment will be on Planck's black body radiation. Yeah, black body radiation. So black body radiation is another experiment that infer light does not behave like wave. Specifically because in order to explain the black body radiation, you have to assume that the light carries energy in its discrete form. It's just this formula. When you write down this formula, it assumes that light behaves like particles. So if you assume that light carries energy, then described by this formula, then you are giving up light behaves like a wave. So in order to explain the black body radiations, the explanation requires light to behave like the particles. It's very similar in argument when you talk about the black body radiation. You compare argument with the photoelectricity effect. The photoelectricity effect is the same. Photoelectricity, you have an experiment, then you try to explain it by using conventional wisdom, light behaves like a wave. Then you fail. Then in order to explain satisfactorily, you have to treat light as particles. Similarly, in black body radiation, you think light is a wave. Then you start to explain the black body radiation experiment using light as a wave. But then you find that no, it doesn't explain, it cannot explain. Then you are forced to adopt a new paradigm that particles, that light behaves like particles and carry this energy. Then we find that we can explain the black body radiation experiment very well. So I have not told you what is the detail of the black body radiation, but basically it's experiments that can measure something, then you try to explain the results using conventional knowledge and you fail. So in that particular case of black body radiations, the experimental result is what we call, the experimental result is not the photoelectricity effect, but the black body radiation effect. The experiment that we try to explain is called R lambda versus frequency. First frequency. Imagine this thing, then you find the particle, the behavior, the shape looks like this. So when you find that the experimental result looks like this. So they try to explain this experiment by assuming light to behave like wave. When they do that, they find that the predictions will behave like this. So this is a prediction of theory by assuming light to behave like wave. So if you assume light behave like wave, theoretically the radiance versus frequency will move like this. But experimentally you see this shape. So which is totally different from what you expect from theory. So now I have to tell you what does this mean. It means is we take a piece of body, let's say a ball. Then you heat it up to some temperature, so say 1000 degrees. Say bearing, say bearing made of steel. You heat up to 1000 degrees, then of course it becomes very hot. Then it will radiate all this heat. You can feel the heat from this. So what they do is each of these heat is a radiations light. So what they do is they measure. They use some experimental setup that allows light to go through a small hole. Then the light will go through this small hole, and then it detect the wavelength. And then how much is the wavelength? So basically, they detect the intensity of light at a fixed wavelength. So you could have say wavelength in say 500. You could also have wavelength at say 560, wavelength at 570. So this hot bearing emits light, very hot light at all wavelength. Various wavelengths, like the sun, it emits light of various wavelengths. But there are some wavelength has high intensity, some wavelength has low intensity. Like I think in our light, I think in the morning, the intensity in the infrared, also in the ultraviolet is less. In the afternoon, in the evening, the intensity of ultraviolet is higher. So different wavelengths have different intensity in the light. So they carry this experiment. Then they found it looks like this. It looks like this. So this is what they call. So instead of I think they somehow can become radiance. So they measure this one, but theoretically you have to explain this one because R lambda is for the experiment measure, and then they just do some manipulation. Then you got so they got this from this. So anyway, you can imagine this to be the same intensity. Intensity of the black body radiations at different wavelength or at different frequency. It's the same. At different frequency or different wavelength is the same. So it's like wave. Right. So for example, wave of say 500 nanometer, it has a frequency of say 10 power of 13 hertz. Wavelength of say 600 nanometer, it has a frequency of I think of say 12 power hertz. So you specify the wave of the light either in terms of wavelength or frequency. It's the same thing. It's just like explain this in terms of radio, this in terms of sound. It's different unique. So they measure this one, then they try to explain theoretically. You assume light is wave, but then they cannot explain. They always have this line that looks like this. So then they feel like then someone come up in 1905 called Planck. He can explain the spectrum. This is called the spectrum. He can explain the black body radiation spectrum by assuming that the energy of the light is given by this formula hc over lambda or equals to h frequency. It's the same formula that I wrote down just now. Then by using this assumption, then he got a very nice curve theoretically that can explain the experimental finding. So the story goes the same. You give away light being like this and assume light to have energy like this, then you explain the declaration very nicely. So then you have the second hint for experiment that light doesn't behave by wave. Its energy, because its energy is discrete, and this is in opposition to light being a wave. So in both cases, in both experiments, light behaves like corpuscular particles that carries energy which is discrete and given by this formula. E equals to hc over lambda. So they finished the part on black body radiation. There's a lot of technical details on this formula, but I don't go into this. It's very complicated. It involves statistical mechanics. But the idea is like this. Then we have this second experiment that light behaves like particles. Then you have a third experiment that also show light like a particle, which is called X-ray. So X-ray is also an experiment that shows the light behave like particles. Yeah. So the X-ray is another experimental evidence that shows that the light is like particles. So the X-ray was discovered in around 1900, and the first Nobel Prize is given to this X-ray. X-ray detection. And then the fourth experiment that shows light behaves like particles is Compton effect. So we have this Compton effect, 2.7, page 75. So this is also like particles, also is the experimental evidence to show light.